Hi, Professor Dikaliu. Thank you very much for switching the time.
Hi, how are you? Thank you so much for your help.
Thank you. Yeah, I'm very much confused with the time difference, and I couldn't actually.
So
Yeah.
it's 5 hours. I mean, from Sydney, probably it's about 2 hours from Hong Kong. Oh, 3 hours from Hong Kong. Is that right?
Yes, yeah, that is right. So actually, you are. I mean, I have to say good evening, right?
No. It's about 3 o'clock here, 3 p.m. here.
Okay. Okay. Good afternoon. The good morning.
Yeah.
Okay.
So how is going? How is going, Professor Kosugi?
Yes, and yeah, I'm enjoying my life here, but I'm still waiting for the approval of my visa for my new position. And
Yeah.
so I still have a very strange position. But anyway, at the beginning of my presentation, I'm going to unveil it.
It's right. So don't worry. Don't worry. It's good. It's good. We had this two workshop organized, and thank you so much.
Yeah, thank you. Thank you very much for your hard work.
So then after the workshop, and let's have a catch up in terms of what we're going to do next.
Okay.
I have some ideas, but I like to get your suggestion first.
No. Please go ahead.
No.
So now, my age, I'm gradually try to retire. It's not true, but
No, don't retire. Don't retire. It's very boring.
no, now this meeting is recorded. Okay, keep you. He said. So Dikai, after my presentation, and I'm trying to stay here longer, but I have to probably around 3 p.m. Maybe 2 hours later, I have to move to another meeting room. It's a face-to-face meeting. So I'm sorry. So the rest of the workshop is completely up to you. And so you can please make, exciting discussions after the presentation. And sorry about it.
Oh, it's okay. It's okay. Fully understand. Fully understand. Sometimes the meetings come up very, in a short notice. So yeah.
And Jose-kun, thank you very much for your work, for the preparation of
Hi, Jose. How are you?
website.
You guys are doing great. No, like I think we have to thank the people at NCAI. They have been so diligent and they have done such a great work.
Sure.
I hope that today's workshop will be a success.
Yeah,
it will be. It will be with the huge support from NCAI and many colleagues in Pakistan. I think definitely it will be a very good event.
Okay, I'll keep quiet until the meeting officially starts. See you again.
Yeah, while we're waiting, and I said, probably it's good for us to think about the other activities. Yeah.
वो प्लान डिस्कस नहीं हुआ।
Hello, I am Hamza Zahid from National Center of Artificial Intelligence. Welcome to the workshop on intelligent robots for practical applications. This workshop is being organized by IEEE International Technical Committee of Robotic Research for Practicality in collaboration with IEEE RAS and NCAI. Now allow me to introduce you to my colleague, Ms. Bisma Sadal. Over to you.
Thank you so much, Hamza. I'm Bisma Sadal from National Center of Artificial Intelligence. Let's first introduce our 6 keynote speakers of today's workshop. First, we have Professor Kazuhiro Kosuge. Professor Kazuhiro Kosuge is the director of the Center of Transformative AI and Robotics, and also a specially appointed professor at Graduate School of Engineering, Tohoku University, Japan. Then we have Professor Dr. Dikai Liu. Professor Dr. Dikai Liu is Distinguished Professor and Director of the Robotics Institute at the University of Technology, Sydney, Australia. His main research interest is robotics with the focus on perception, motion planning, physical human-robot collaboration, and design methodology. Then we have Professor Dr. Yasser Ayaz. Professor Dr. Yasser Ayaz is the Chairman and Central Director of National Center of Artificial Intelligence. He is also the founder and president at IEEE Robotics and Automation Society, Pakistan. He is also the professor of artificial intelligence and robotics at National University of Sciences and Technology.
Fourth speaker of our workshop is Dr. Wajahat Qazi from Comsharsh University, Lahore. He is an assistant professor in charge machines and robotics in Department of Computer Science, Comsharsh, Lahore. He served as a co-founder executive director of ECOG Private Limited. Fifth speaker of our workshop is Dr. Yasir Niaz Khan from University of Lahore. Dr. Yasir Niaz Khan is the assistant professor in the Department of Computer Science at the University of Lahore. Sixth speaker of our conference is Dr. Umar Asghar from Nash University. He is working at Department of Robotics and Artificial Intelligence at School of Mechanical and Manufacturing Engineering, SMME, Nash. He is new engineering researcher with PhD engineering specialized in brain-computer interface.
Thank you so much, Hamza. So these were our 6 keynote speakers for today's workshop. Now, allow me to welcome Professor Dikai Liu for an introduction to IEEE Technical Committee of Robotics Research for Practicality. Over to you, Dr. Dikai.
Okay, thank you very much. And it's really, really my pleasure to join this workshop. So I'm going to share my screen. So can you please allow me to share my screen?
Yes, sir, it's done.
Okay, can you see my screen here?
Yes, we can see your screen.
Okay, thank you. So on behalf of Professor Kosugi and Professor Brooks and Professor Dean and Professor Biskov, and I'm going to give a very short introduction to the IEEE TC of robotics research for practicality. And this is a TC initiated jointly by these 5 people and in 2018. So now it's about the 3rd year. So we have had many activities on this TC. The reason we set up this TC are here. One, in robotics research, we have already made a significant progress. And the impact in research and to community and the industry through applied robotics research. But the issue here is that the pace of applying intelligent and autonomous robots in real-world applications is quite slow. So we have not seen many autonomous robots practically deployed or available in the market. So researchers in robotics may not fully appreciate the challenges related to applying robotics research in real-world applications. So those are the reasons we really set up this TC and in 2018. Here are some examples here. Sorry, just can you see this video? Excuse me, can you see this video? Just in case you cannot see it, I have to change it, yeah. So, hi, Professor Kosugi, can you see this video?
Yeah, I can see your video.
All right, is that full screen or just a small on the screen?
No, it's a small screen. It's not a full screen, but we can see.
Okay, so that's what I like to confirm here. So, so I like to share the full screen. Just a moment. I just come to this screen. Okay, so. Okay, so this is one of the many examples of robots for practical applications here. And what you can see here, the robot is used or is developed for application in confined space. But in this kind of confined space, it's very challenging for a robot to operate fully autonomously. So we have been developing this robot for 5 years, and we had so many success. At the same time, we had so many failures, both in the lab and on the bridge. So you can see the robot here. So the question here, raised here, is that we have done many research here, but in reality, why do we need so many tests in the trials in the lab, in the bridge? So can we do something better in the lab and then make it successful in the bridge? This is the question we have been asking ourselves, but in reality, it's very difficult, mainly because of the practical application applies so many constraints to research here. So then here is another example. Here is another example of human-robot collaboration. You say we have the robot here, we have a person here, and working together with this robot, and we have done many trials with this robot. But by the end, there are still many times we got the robot not able to work together with people. So again, this is another big problem of robotics research. Although we have done a lot of research in the lab and we tested it works, but in reality, if we put this robot into real application, it still fails. So then what can we do with this kind of research here? For example, you say the person is playing with the robot, but when the workers start to use this robot in real industry applications, and you can see it's a very challenging environment, the robot may fail, then what can we do? So from the robotics researcher's point of view, one more example, this is from Professor Kosugi. So research work here, probably Professor Kosugi can explain more, which is a robot here to support a person and doing the assembly in the assembly line here. Again, many research questions of human intention estimation, real-time motion planning, and the first version was installed in the factory environment and has been used for several months. But the new system has been developed and used for several years, and it requires a long time from the research lab to the real industry applications. So this is one more example. Another example here is about the many robots working together for container handling. So this is the bigger robot here, and we have 40 such robots operating in the port to move containers 24/7. But again, the algorithms in simulation works very well. As soon as we implement the algorithms in real industry applications, we have to make a lot of changes. So again, this is another example shows the difference between fundamental research and applied research here. So the scope of the TC really is basically we provide a forum for researchers and engineers to discuss the challenges related to applying robotics research in practical applications. Critically reflect challenges beyond the fundamental research, and also how we're going to communicate about the quality of research being practical in robotics research, and also discuss feasible ways of developing robots for real application and effective ways of academia and the end user or industry collaborations. So this is the scope of this TC. Then we plan the many activities here, for example, workshops and equal or and IROs invited and special sessions and symposiums in conferences and special issues in journals and the joint workshops with other TCs as well. And also we engage with the industry and the government in various ways here. So this is where you can find more information about the TC, and this is the QR code you can scan and then just visit the website, and also at the same time you can just register as a member of this TC. So you are warmly welcome to become a member of this TC, then we can form a consortium to communicate and discuss in the future for many events. So, okay, so this is my very quick introduction to this TC. And if you have any questions, please let me know, and then I will just answer your question. If not right now, probably during the workshop or at the end of the workshop. Thank you very much.
Thank you so much, Dr. Dikai. That was great, insightful talk from your side. Allow me now to welcome Professor Dr. Yasser Ayaz, the chairman of National Center of Artificial Intelligence, for a welcome speech. Dr. Yasser.
Good morning, everyone. It is nice to see you all. Special thanks, Professor Dikai Liu and Professor Kazuhiro Kosuge, for making time to grace this occasion and to help us organize this workshop. I think our announcer made a small mistake in the beginning that actually it was 2 opening speeches in the beginning and then Professor Dikai Liu's speech, but like she had introduced Professor Dikai Liu first. But anyway, this kind of thing happens at the workshop, and it's good that we got an introduction to the conference and like the introduction to the committee of robotics for practicality in the beginning, so everybody knows what the targets are. So it's a great privilege and great pleasure for a unique, one-of-its-kind workshop. And actually, in the beginning, what I would like to first of all say that the starting of IEEE RAS Pakistan was actually based on one of my discussions with Professor Kosuge. And I was visiting Japan at that time, along with my students. And actually, myself and Professor Kosuge were driving, and he was taking us to dinner very kindly. And at that time, we discussed about RAS and some of its activities, and I decided that it would be a good idea to take his advice and also start RAS activities in Pakistan. And Professor Kosuge, of course, is a pioneer of RAS, many RAS activities, and one of the most key, I think, figures in RAS in the world. So having been the director of Division 10, and of course, the vice president of IEEE TAB just in the last committee. And of course, the past president of IEEE RAS, and above all, my teacher. So this is why I'm really honored to actually see you here. And Professor Dikai Liu also, thank you for making time and gracing this occasion, and thank you for a very kind introduction of this conference, of the committee, of course, of the robotics for practicality. I think it's a very important subject, and many people, when I came back to Pakistan after my PhD from Tohoku University in 2009, I heard a lot of people say in Pakistan that maybe, they're not sure how much robotics is required for the developing world. Maybe for the developed world, for the industry, for the manufacturing, for many other things, robotics is required. But how much is it required for the developing world? And it took us some time to explain to them and to establish new laboratories, get funding from the government, and also start new programs. And with time, people started seeing the importance of robotics for our region. So as I'll later on explain in my own talk as well, for rehabilitation robotics, for medical robotics, for many other fields in robotics, it's actually a very important area. And I think that IEEE Robotics and Automation magazine has also done a series on BRICS countries, for robotics for BRICS countries. A really critical area for the entire developing world. So I would just like to thank everyone for making time for this workshop. And I think it's a really proud privilege to be able to welcome 2 of the very senior professors from abroad, especially my teacher, Professor Kazuhiro Kosuge. Thank you, both of you, for making time for this workshop. And now with this brief introduction, Professor Kosuge, could you give some welcome remarks, please?
Okay. Thank you very much, Professor Dr. Yasser Ayaz. And now I think that starting from July or this month, you'll be in the same position as mine, especially appointed professor of the Tohoku University, right? Good morning, good afternoon, everybody. I'm Kazuhiro Kosuge, actually a friend of Professor Yasser Ayaz, and I'm very happy to be here to have such an opportunity, and together with the Professor Dr. Yasser Ayaz and his staffs of NCAI. And especially I'd like to thank everybody for the preparation of this workshop. And actually, this idea, the idea of creating this workshop came up to us when I visited Professor Dika Liu's laboratory in Sydney, right? I was so impressed with his research outcome directly applied to real issues in real environments. At that time also, we are suffering from the practicality of our research. And I thought that we came up with a very nice idea, but unfortunately it was not commercialized. I have a lot of experience like that. So we thought that it's a good idea to start this technical committee. And fortunately, very well established scholars are willing to join us, like Rodney Brooks, Rainer Bischoff. And so we finally, in 2018, we could successfully started up, created this, the creation of this TC was approved. So I'd like to thank all of the participants of this workshop for joining us. And I hope that you will get something different from this workshop. And I hope you will be a member of this technical committee. Thank you very much. And I think that Dika has, you've already given everything. So next presentation will be given by Professor Yasar Ayat. And I think that you have 40 minutes of your presentation.
Thank you. And a little more time is always useful. Let me share my screen.
Thank you so much, Professor. Now we would like to introduce, we would like to invite Dr. Professor Yasser Ayaz for the introduction to IEEE Robotics and Automation Society presentation. Over to you, sir.
Thank you, Visma. You can see my screen, right?
Yeah,
Yes,
we
sir.
can say your screen, yes.
Right. So I'll briefly introduce the IEEE Robotics and Automation Society Pakistan. As I already mentioned during my opening remarks, that it was actually during one of my visits to Japan and in one of my conversations with Professor Kosuge that I got finally, got the courage to actually start this kind of a society in Pakistan as well. We were having robotics activities for a long time in Pakistan, but to formally do it in the manner that it is done with IEEE, and when I studied the model of IEEE RAS, I actually realized that the way that it is structured and the way it has committees and like a technical activities board and a conferences committee and other sections. So it gave me a really good idea about how society should be structured. So when you see this presentation and when we go through the slides, you'll realize that we have tried to actually copy as much of the model as possible. The international model, we've tried to keep the model the same, only make it at the Pakistan scale. So first of all, IEEE Robotics and Automation Society Pakistan is actually a joint chapter of Islamabad, Lahore and Karachi sections of IEEE. So in Pakistan, there are three IEEE chapters. So these are Islamabad, Lahore and Karachi, and there are some subsections, there are some subsections other than these, which are going to become full sections later on. So right now there are three sections. We have actually combined the three sections and made one chapter, a joint chapter of IEEE RAS, so that we can actually link all of the robotics and automation societies in Pakistan together in one section. So I think the numbers may not be very current, but last time I checked, it was we had 123 professional members. I think the time when we started from about 12 or 14 members at that time. I think 12 members we registered ourselves, and a couple of members were existing before that as well. So there were not a lot of members in Pakistan at that time. But the professional members, in most societies in Pakistan, majority of the members are usually students. And here we've been able to actually gather professional members as well. So other than this, there are graduate student members and also the student members. So it was founded in the end of 2017. And I think our first executive committee meeting was in January 2018 in Lahore at that time. And this is a distribution of members that in Lahore and Islamabad, there is a major chunk of members, and in Karachi also, we have some membership. Also, we have been able to start around 13 chapters in universities. So like these are student sections. And you can understand that like with this, there is a relatively much bigger student membership base, including graduate students, as well as the undergraduate students who participate in these chapters of IEEE RAS in the universities. The structure of IEEE RAS, as I mentioned before, it really impressed me, the overall international structure. And on the same model, we decided to actually base the structure of IEEE RAS Pakistan. We've introduced a couple of new positions, but a lot of the positions you see are similar to what exists internationally. For example, like I have the privilege to be the chair, and I founded the society as well some time back. So we have a technical activities board, a small technical activities board under whom there are technical committees. So like we have the chairs of various committees in the technical activities board inside that. So Dr. Umar Ahmed is actually leading that from Comsat University Islamabad. We have vice chair conferences, Dr. Yasir Niaz. He's here today and he'll be speaking. He'll be giving a talk today as well. So you'll get to meet him very shortly. He's currently with the University of Lahore. Like he basically like links together all the conferences and oversees like when people are submitting their like initial proposals, making up the proposals, submitting them to IEEE, their whole approval process, and then monitoring the conferences throughout the time that they actually like they complete all the proceedings, and the proceedings are actually uploaded to IEEE Explore. So the conferences part actually looks at that. Then we introduced a new position, which is of vice chair competitions. So in Pakistan in particular, and in many parts of the developing world, competitions of robotics are actually very popular. So other than IEEE RAS, we have done a number of competitions as well. I think just before the pandemic in 2019, I helped organize a competition in Tashkent in which we brought about 4,000 students from like a majority Asian, African countries, and some from European countries as well. And this was all sponsored thing by an organization called ComStack, which is a commission for science and technology based in Pakistan, but it's a union of many countries. So it was about 4,000 students from 31 countries that we had actually brought together. So we actually play our role as like a partner in that kind of competitions, and also we like organize our own competition. So in Pakistan also we have organized our own competition, not at that big a scale, but still things for students to come together and actually apply robotics. And I think this is one part very critical for robotics for practicality as well, because this gives hands-on practical experience to normal students. Even if they don't have access to a very advanced lab, they can participate in robotics competitions and actually benefit from that. Then we have the regional vice presidents. So we have functional vice presidents and we have the regional vice chairs. So in the regional vice chairs, we have from Islamabad, Dr. Umar Asghar. He will also be speaking today. So the regional vice chairs look after all of the activities. They oversee all of the activities within their respective regions, and they also represent the IEEE RAS as a part of the executive committee of the local section. Like for example, Islamabad, Lahore, and Karachi, there is 3 sections. So we have 3 vice chairs who represent in each section. In Islamabad, of course, I myself also participate, and so it's myself and Dr. Umar, both of us. And in Lahore and Karachi also, whenever I am visiting, whenever I get the opportunity, so of course we meet the IEEE leadership and work as part of their ExCom as well. So in Islamabad, there is Dr. Umar Asghar. In Lahore, there is Dr. Wajahat Qazi. Dr. Wajahat Qazi will also be speaking at this conference later. From Karachi, it is Dr. Muhammad Khurram. And we also, last year, we introduced a new position called the Vice Chair of Memberships. We had this position earlier announced, but recently we appointed Mr. Tanveer Bukhari in this position. He's one of the most active members, who was previously the Central General Secretary. And based on his activities and work, he was actually upgraded to this position. And there are some other positions that we would like to appoint people on later on as we get more vibrant members to actually work. And to coordinate, to help me with the coordination effort, we introduced a post of Vice Chair Coordination. And for that, Dr. Noman Nasir from Islamabad is working with me. So, we're trying to link with, for example, the special interest group on humanitarian technologies site. So we've got a RAS site coordinator who actually looks after the activities pertaining to this special interest group. And we also tried to have a representative for WIE, for the Women in Engineering. But at that time, when we submitted the proposal for having the structure of IEEE RAS, So that was not it was not supported at that time, in the petition. But we are thinking of a way to actually have a dedicated appointment for women leadership in IEEE RAS as well. So with this brief structure, so let me give you a glimpse of some of our activities. And we have, for example, just recently we have organized in March 2021, the International Conference on Artificial Intelligence. We had actually initially planned it for September or October 2020, but then we kept hoping that maybe the pandemic situation will subside and we'll be able to do it physically. But since the pandemic seemed to be not easing off, and even though the infections got reduced in Pakistan, but still it was dangerous to actually gather a lot of people in one place. So we actually had to do it online. The Federal Minister for Science and Technology, Mr. Fawad Chaudhry, was actually kind enough to actually grace us at this occasion, and we were able to leverage support from the government side as well for this conference. It was also sponsored by the Higher Education Commission of Pakistan through the funding of National Center of Artificial Intelligence, which I am also leading in Pakistan. We also did a webinar series just recently, in 2020. We actually did it was announced in 2020, and still, of course, we keep doing webinars in 2021 as well. This webinar series, which I'm showing, is from 2020. We were able to get speakers from some international universities as well, and of course, some of the leading Pakistani universities too. And just before the pandemic, we also did a seminar on artificial intelligence, which was organized in Lahore. We also do technical workshops. So these are you could say it's like paid workshops for students. They actually have a fee to actually attend these workshops, but IEEE members get 50% discount on the workshops. So IEEE, from the platform of IEEE RAS and the universities that have chapters of IEEE RAS, we jointly organize this kind of workshop. This workshop was organized by me at NUST, and we had this workshop in which we tried hydraulic and pneumatic actuators and hydraulic and pneumatic systems and their applications in industrial automation, and how they're applied to robots, which, for example, lift heavy weights in the industry. So this was a technical workshop which we organized. And also, this is me again, but some time back when I used to have longer hair. And we have an internship program as well, in which the prominent IEEE student members who have good contributions towards IEEE RAS within their student chapters are actually given the opportunity to come into another university where we have one of the IEEE RAS leaders, and we connect a few interns during the summer, and we actually get them to do internships. So we have welcomed students from different areas. For example, in this particular picture, the student standing with me, he's a student from FAST University, and he's the vice chairperson of his local IEEE RAS chapter. And he was attending the internship with me at Islamabad in RISE Lab. So, and there have been other internships as well of this type. We also welcome students for educational visits to our university. This is my laboratory. You can see here in the center. And we welcome students. And this was, I think, a visit of IEEE students from IEEE Islamabad section. These are students from various universities, and they visited the Robotics and Intelligent Systems Engineering RISE Lab, as I call it. So I'll be giving the presentation about that later. But we also organized several workshops and activities. This was one of the workshops in Lahore. And as you can see, some of our industrial collaborators like Devrim Technologies and also Advon actually co-sponsored the event as well. So they financially sponsored the event as well, and they actually participated in that. This was a big event in Lahore. And we have this regular workshop, which we do 2 times a year. And this is in collaboration with the University of Kaiserslautern in Germany. And this particular session was held in 2018 at LUMS in Lahore. But the workshop takes place every year. So in 2019, 2020, we've been holding this workshop as well. So the session in Pakistan is supported by IEEE Robotics and Automation Society, Pakistan. And there are 2 in a year. So there was one workshop in Pakistan and another one in Germany. Then there is we have multiple other activities. I mentioned that we organize robotic competitions locally as well. So this is a glimpse from one of the competitions. You can see on the left bottom that there are this is robot sumo on the leftmost, and then the line following robots. And this is me and Dr. Wajahat Qazi, of course, giving our keynote talks and speeches there. And a lot of students, very excited students. You can see that they even find it hard just to sit on their seats, and such an exciting contest taking place in front. So this is, we've realized a good way to involve the students more and more towards the robotics activities, to actually indulge them into competitions. And there are other activities like various kinds of workshops. I think I'm already taking too much time, so I'll just shorten it here. We have several kinds of workshops and activities. This was in Canadian College for Women. It's an introductory workshop to senior college students before they enter into their robotics focused degrees. And we regularly represent in various executive committees. This was in Bahawalpur subsection. So to encourage them to also develop a vibrant society in robotics. And this was a dedicated workshop that we did in the early days of IEEE Robotics and Automation Society in February 2018. So this is this was an informative workshop, and we also brought some practical robotic arms to actually demonstrate some of the robotic capabilities to students. So and this is, of course, our first executive committee meeting, which we had in Lahore in 2018, in January 2018, which I mentioned about. And we like whenever we are gathering at some place, like in a workshop in Karachi, Lahore, or Islamabad, we actually organize an executive committee meeting alongside it. So this is just a brief introduction of IEEE Robotics Automation Society Pakistan and the sort of activities we do. We are yet a small section compared to a lot of bigger sections in the world, but we are trying our best to actually make use of the knowledge and the experience from the international body, the IEEE RAS, and base our activities in a way that all of our activities are aligned in the same manner and aligned towards the same kind of activities which take place in the international IEEE RAS section as well. And it's a great opportunity. And as I said, one of its kind, first of its kind workshop to have the opportunity to welcome the esteemed professors for this international technical committee and to join this kind of workshop. And we hope to hold more such events in the future as well. Thank you.
Thank you so much, Dr. Yasser. Now we will start with our first keynote speech. And for that, we have Dr. Yasser Ayaz from National Center of Artificial Intelligence. And the topic he'll be speaking about is robotics for rehabilitation. Over to you, Dr. Yasser.
Thank you. So it's me again. So apologies for too much me in the workshop today. And I'll briefly tell you about our research for robotics for rehabilitation. As was introduced by Bisma shortly in the beginning as well. So I am leading the National Center of Artificial Intelligence in Pakistan, and I'm also a professor and the founding head of the Department of Robotics and Artificial Intelligence at NUST. So I founded this department after coming back from Japan, and initially we worked with the manufacturing department and the mechanical department, and eventually it evolved into a proper department of robotics and artificial intelligence. And in 2016 we were given the opportunity by the government of Pakistan to actually compete for a bid to actually set up a National Center of Artificial Intelligence in the country. And we were lucky, we were fortunate to win the bid in all across Pakistan. There were more than 180 universities trying for laboratories and the central setup of this. And we were lucky that we came out at the first place, and we actually got to host the center secretariat of IEEE, this center, of course, like IEEE RAS is there, but we actually won the central secretariat for the National Center of Artificial Intelligence, along with two major laboratories. So one of them is in the area of intelligent robotics, another one in the area of deep learning, and we've got our laboratories in medical imaging and diagnostics, also in Islamabad. And we have our presence in, other than the federal capital of Pakistan, which is Islamabad, we have presence in 3 provincial capitals as well. So this is Peshawar, Lahore, and Karachi. And we have various laboratories focusing on different areas, which include applications of both robotics and artificial intelligence. So with this kind of setup, it's around 200 and more than 200 researchers, I think around 222 technical research officers with, I think, 37 to 38 PhDs that are actually located in all of these laboratories distributed among these labs in Pakistan. So I centrally look after this setup. And of course, I'm also the department chair. I was the department chair, and right now I'm also the director of this center, the part of this center which is located in NUST. And I've been the department chair for around over 10 years, I think, for the Department of Robotics and AI in Islamabad, in NUST. And this is my laboratory. RISE lab is the name of my lab. It's called the Robotics and Intelligent Systems Engineering Laboratory, RISE. And I still, of course, head this laboratory and I look after the research here as well. My presentation today will be focused towards the kind of research that we are doing in this laboratory and how it is focused towards rehabilitation. You can see that we've got 4 major research areas like mobile robotics, cybernetics and bionics, legged robotics, and human-robot interaction. And actually, in rehabilitation, all of these 4 areas actually come together. And in all of these 4 specializations, you'll see work we've done related to rehabilitation. The research theme of the projects that I'll be speaking today on is regarding how to integrate artificial intelligence into rehabilitation technologies in order to help people with severe disabilities. So one of the initial projects that I started venturing on when it came to work in rehabilitation, so I actually started looking at like this company organization which is based in Japan. It's called Sakura Wheelchair Project. Actually, it's an NGO. It's a non-government organization located in Tokyo, and it's like the parent organization is a company, a wheelchair manufacturing company called Saito Kobo, and they have this you could say humanitarian project in which they try to help severely disabled people, especially in the developing world, by providing them with wheelchairs. So when I saw some of these activities, I already had it in mind that I wanted to develop a wheelchair which has autonomy, which has some autonomy. It could have laser rangefinders and cameras fixed on top of it. It could run on RAS or other robot operating softwares, and like have some sort of autonomous functionality in it to better assist people with severe disabilities. So we joined hands with Sakura Wheelchairs of Japan, and NUST and Sakura actually signed a memorandum of understanding in which they supplied some of the wheelchairs to us. So this, for example, wheelchair was provided to us through that collaboration. So, and we have 2 of these wheelchairs that were actually donated to us for the sake of research. And then, of course, NUST sponsored a lot of the sensors that we actually planted on this wheelchair, and some of the computational facilities also. So we have a laser rangefinder, a stereo camera. This is a mobile ranger stereo camera. And at the back of the wheelchair, we have this computing system in which we have actually combined 2 computers, one looking after the vision and graphics acceleration, etc., and the other looking after the control and planning part. So we have got this kind of a system in it, and it runs on the robot operating system RAS. So this wheelchair, of course, has capabilities like environment perception using the sensors that it has on board, path planning, navigation, a human interface, and some level of autonomous control. And of course, we keep developing more and more like applications, more and more projects on this wheelchair. So I have already described the computer. So what we've done is that we haven't removed or changed the low-level drive computer of the wheelchair. So this is a kind of system that you can actually plant on top of an existing wheelchair. And we just removed the joystick. The regular joystick of the wheelchair has been removed. And we connected the joysticks portal with this computer, which is at the back. So the auxiliary computer and the wheelchair computer, which are here, auxiliary computer is the one which looks after vision and graphic acceleration, and the wheelchair computer is the one which looks after planning and control of the chair itself. And the low-level drive controller is there, which is the default controller of this wheelchair. So now the default controller, the low-level drive computer, is actually given the commands from the wheelchair computer, and this actually has input going into the joystick portal, and it drives the wheelchair around. And you can connect it to the USB joystick if you like, but you can also run it with just using your normal mobile phone, and any Android phone or iOS phone. You can use it to drive the wheelchair around, or you can actually the wheelchair can follow you if you want. So there are a number of functionalities. You can also drive it using commands from your human brain. So this is like the general purpose architecture that we made for it. We tried our best to cut, not to cut through a lot of electronics of the wheelchair. So the only thing that we've actually disturbed from the wheelchair is the portal for the joystick, that we actually took the wires out from there and put our own connector in. But you can imagine that from the encoders of in the wheels, we did not cut the wires of the encoders to give signals separately to our computer, and we have no way of decoding that command, which is actually coming into the low-level drive computer. So when we drive the wheelchair, we actually have to rely on visual odometry. Like, we don't get the signal from for dead reckoning and for odometry. we don't get the signal from the encoders in the wheels. We actually have the IMU on board that tells us something about the reckoning, and we also rely on visual odometry. Like we rely on the input coming into the cameras to actually do visual odometry, and then the simultaneous localization and mapping. So this is the general structure. So like the Vision PC is the auxiliary computer. We've got the Cobra PC, the central Cobra PC, which has the RAS based interface, and this is actually running the main software for control and planning. And we can connect an HMI tablet, the human machine interface tablet, with it. So just like a very human friendly control, you can actually give commands to the wheelchair. But if a person, for example, is not able to use the tablet, and if it's a severely disabled person, he can actually drive the wheelchair, he or she can drive the wheelchair using like just the movement of the eyeball. So like we can wear an eye camera interface, which is locally developed in the lab. Also an EEG headset is used like some also to drive the wheelchair, but it requires some training for the person to actually learn how to give those EEG commands, which will be interpreted by the wheelchair to turn right or left. And we can actually choose from a series of commands based on the patient's requirement when this thing actually becomes commercialized. And like in the Cobra PC, we also have inputs from a stereo camera, from the SICK laser LMS200, the wheelchair drive circuitry, and all of these, they connect with the Cobra PC. We also developed a proposal jointly with Carnegie Mellon University in the US, and we submitted to both countries, in Pakistan and US as well, for putting a manipulator on top of the wheelchair and actually navigating through doors, etc. We've also done some research on detecting doors. So, but to open a door, we need a manipulator on top of a wheelchair. But so far, the funding is not with us. We haven't received it yet. But in the future, if we receive that funding, we hope to do that research as well. So this I already mentioned to you that we rely on visual odometry because we didn't cut through the wires there. So we've developed the motion planning algorithms, and for this we develop RRT Star Smart, PGT RRT Star. So a number of these are just 4 of them. We actually developed a lot of these algorithms, and in global path planning, they are I'd say they have citations from a lot of parts in the world. So we were lucky that we actually got some ideas right in these planning algorithms. We also made motion planning algorithms for dynamic environments. This is also variants of RRT star based motion planning algorithms, but its practical application is towards this kind of mobile robots or wheelchairs navigating in the human environments. So this is the practical application of that. Let me show you a brief video of the project. This is the team from Japan visiting us along with some partners in Pakistan. So these are some user control options. And you can see that first is a cellular phone based control. So incidentally, this is what the company in Japan liked the most, this interface, even though it's very, very simple. And we just made it for our convenience during experimentation. But they really liked it that you could actually drive the wheelchair and park it somewhere, using that mobile phone. So this is a wheelchair camera. You can see that the person is wearing an eye camera interface, and based on the movement of the eyeball towards right or towards left, you can actually drive the wheelchair around. And you can see that here we are doing visual odometry and also simultaneous and localization mapping. So we are actually mapping the environment as the wheelchair goes. It actually gets the camera input, and from the camera input and the SICK laser, it actually jointly, with multi-sensor interface, it combines the two, and it results in that odometry output. This is the wheelchair is being steered by an EEG headset that this person is wearing. This is my student Ali. He is wearing this. So this is teleoperation mapping. We can of course drive the wheelchair by ourselves using the mobile phone interface or any other device like that, or the wheelchair could be left to wander around and actually develop that interface. So this is RISE Lab. The wheelchair is driving around in RISE Lab, and it's actually mapping the environment as it goes along. And then based on that map, or while we are also discovering the map, we can actually give it commands like this, that move in one direction or the other direction. It can actually map the environment, and we can control the wheelchair by ourselves as well for that. So this was just a brief glimpse into this project, and this is some pictures again from the Japanese team that visited us, and we are happy that they actually liked our project, and also to connect more with the local community, we develop prosthetic devices as well. And this picture you can see, like this lady, she accidentally got her hand cut off in an accident in her home. She's living in a village, and she was actually working on one of the you could say like local, like there's a system like a turning wheel, you can say, in which they cut fodder for animals to actually feed the animals which are there in the village farms, right? And accidentally her hand went through the cutting machine, and it was actually cut off, and her father brought her here to Islamabad. And actually when she went to the hospital, doctors told her that for EMG based multi-fingered hands, they could refer to us. So, and on the left is Ramsha. She visited me in Japan as well. Professor Kosugi may remember that she was one of the 10 students who visited with me to Japan as well. So on her hand, you can see like this is our own locally developed EMG interface, the electromyographic interface, which can actually read signals from our hand. And we've actually developed a various number of devices, like our own EMG interfaces. Like, for example, this small sensor is the basic sensor around which there is a whole lot of circuitry, bioamplifiers, etc., which we actually use to give command to our computer. The small computer also has to be worn on the body of the patient because we want to make it totally portable. So this is one of the things, and this was one of our first prosthetic hands that we developed. So this was tendon-based, that we actually had motors embedded inside the palm. And as you can see from this image, that for this lady, for example, the hand was cut off right at the wrist. So we don't have a lot of area in which we could put servo motors, you know, in the back area of the arm. So all the motors and everything has to go inside the palm of the hand. So we actually used DC motors inside this, and they were not with servo control and like included in that. So that we developed ourselves, and we put in our own portable computer, which was mounted on the arm which the person is wearing, which the patient is wearing. So this was the first one. But the problem with this kind of hands is that they are not very good at grasp. Like the grasp is not very strong in this kind of manipulators, because they are using, you know, like we use the fishing line to actually make tendons inside the hand, which actually grabs things. So there are two problems. One, the grip is not very strong. And the second problem is that actually the fishing line cuts through the 3D printed material. So with time, there is a lot of wear. So because of the wear and tear, tendons become loose, and this is why the hand requires continuous adjustment. Like every month, it has to be adjusted. So we developed a second model, which is based on, this is a linkages-based hand. So inside this hand, there are gears, and there's proper motion transmission mechanism. So it has much better motion transmission, with all 5 fingers, and we still try to keep the motors as much as possible going into the hand, and there's some circuitry is hidden inside this part, this one. And we've also embedded a small camera here to give inside the palm of the hand to actually enable us to recognize the object which we are trying to grasp, and we should be able to make various postures with the hand to actually be able to grasp it. So there is EMG based control. You'll see some demos of it here, and you'll see some clips in this video. And so far, this hand is not tested on the patient, but with time, as we develop a new socket, we are working on a new concept for a socket. We'll test it practically as well. So you can see it can do pinch grasp, it can do enveloping grasp, Anglo-Bentis grasp. So a lot of these grasps are possible, and at least with a small amount of water, we tried that this hand can actually grab and lift the objects as well. So this a lot of tendon-based control, this kind of grabbing things which have weight in it is actually not very possible. So this is a precision grip, a pinch grasp actually. So various kinds of grips are possible with this hand. This is a tripod grip. So this is the students who are working with me in this, and Ramsha, you can see here on the left. Also, in Ramsha's own thesis, we also developed this kind of interface, which is like a tactile sensation interface. So one of the problems we were facing when we worked with prosthetics is that we realized that the patient didn't really feel one with the hand. And there was a lot of cognitive workload for the person to look at every object and to visually see whether it is being grabbed correctly or not. So we developed this kind of interface in which there are 5 sensors, on force sensors on the fingertips. And this signal is going back to a band here, which actually has 5 motors inside it, and they vibrate at different frequencies depending upon the force which is felt at the fingertip. So we actually done some papers on this as well. And one of the good things that we actually had is that we've tested it on about 32 patients in the Armed Forces Institute of Rehabilitation Medicine in Islamabad, Rawalpindi, actually. And one of the feedbacks that one of the doctors gave us is that some patients commented to the doctor that they actually feel as if their real hand has come back. Once they start getting the feeling from the hand that now something is touching their finger and they can feel that touch. So one of the patients remarked that maybe it makes him feel that as if now they can feel their real hand again. Even though the interface is different, it's only a vibrating motor. It's not like a proper feeling going to the nerves, but still the brain learns to adapt to that and it interprets that. So this is the wearable band with 5 motors inside it. It took some research to find out with what sort of distance should be there between all of them, so that the patient could flawlessly recognize which fingertip is right now being touched and how much force is being exerted. So we did some work on that, and this is the interface we developed. We're also working on human exoskeletons, like hand exoskeletons, and we've built one for the upper arm as well, for the shoulder as well. But the one that is there in the picture is for the hand, and you can see it in operation. The person here on the right is wearing a myoband interface, and right now, with the signals from this myoband, he's driving the exoskeleton being worn by the other person. So in this, this kind of exercises are possible. But we can also develop interfaces, probably not worn on the same arm, because of people who've gone through paralysis are actually sometimes their neuro interface of the same hand is not very good. But we could actually interface this with EMG signals from the back of the body or from the other muscles, which actually could help the person use their hand using this kind of exoskeleton. You can see that this is a relatively heavier glass, but it will be possible to grab it and hold on to it using the exoskeleton. Even though this is only a acrylic based interface, we try to make it as lightweight as possible. So we also worked on soft actuators, and the top one, this one here, is the soft grasping mechanism, the soft actuator. This is for a 3-fingered hand, which actually grabs onto small soft objects, like for example this bottle. So a normal robotic hand may even crush this bottle because it's very thin and very easy to break, very easy to crumble if a normal robotic hand grabs it. What we did is that this is a pneumatically operated system, which we actually make the regular robotic gripper grab onto this hand, and its opening and closing is we can build a separate PLC input with this industrial manipulator to actually grab it. But the reason why I put it here, because this is not rehabilitation, but the reason why I put it here is that we've also developed a version of it which can be used as a 6th finger. So this is human augmentation, which could actually be used, for example, if a person has had paralysis and he's not able to use his fingers to actually grab onto something. So this 6th finger could be used for that. 6 fingers, as you know, already exist, and there's a very well-known startup by a very good friend, actually, Professor Domenico Protagiso from Italy. And one of my students who was working in his lab actually developed the first 6th finger, which was electrically actuated. Now he's Dr. Irfan Hussain, his name is, and he's working in Khalifa University in Abu Dhabi now. But we developed another interface. I was part of his committee in that, and later on I got the idea that why don't we develop an interface which is pneumatic, which is not electrical controlled, and pneumatics would actually enable us to make soft actuators which will actually be able to grab objects without really damaging them. So also we developed prosthetic legs and feet. So this was our first project on that, in which we were lucky enough to actually win a prize from the Asia Pacific region. So in Asia Pacific ICT Awards, we won the first prize in Sri Lanka. It was in the year 2018, I think. And this is a transtibial active prosthetic foot. And you know that Professor Hugh Herr, for example, is very famous from MIT for his prosthetic feet. But in Pakistan, when we tried to develop similar prosthetic feet, the problem we faced is that leaf springs are not easy to manufacture. So his prosthetic limbs, his prosthetic feet are actually designed with leaf springs. So we developed a system with series elastic actuation and linear springs, which actually mimics the same kind of motion which is done by that leaf spring based system, but is cheaper to manufacture for the developing countries. So this kind of system we made, and we actually won the first prize in Asia Pacific region for this as well. But you see, this system, one problem was that it was heavy because of the motor and the gear systems and all that going inside it. And the second problem was that this only was for the ankle joint. It did not actuate the knee as well. We have a lot of patients in the like in the hospital which actually require actuation for the knee as well. So we developed this new system in which you can actually see that the patient is wearing this system is actually like walking around with the actuated knee. So there isn't a motor. You won't be able to see a motor in there. So what is actually happening is that, with the walking speed, the spring gets charged. Like when the person actually puts his foot down and he actually moves his body forward, he's actually charging the spring, which will actually, whenever the moment he lifts up his leg will actually kick forward and come back into the position where the foot actually places on the ground. We've used some AI theories for optimization to actually, get the right, you could say, springs in. And now the person can walk at variable speeds, and you don't have to like train it or tune it at some specific speed beforehand. So now this can be used. So this is very useful for patients in Pakistan because the only other locally developed facility they have in Pakistan is a wooden leg. And on top of the wooden leg, there's a small metal stud. So this is a good example of how we can use robotics and mechanics and actuation actually to improvise and develop technologies for them. So this was mostly physical rehabilitation. I'm entering the last 3 minutes of the talk, so I'll just quickly wrap this thing up. But this is one of the projects called RoboCup. It's RoboCup, is an international competition. And the team from my lab is actually the first one from the South Asian region to actually qualify for the Standard Platform League. From 2014 to present, we've been continuously qualifying, and we've been on TV all over the place. So students who come to our laboratory, so this is me again, my old picture, the old me. The students who very frequently, students used to come to our lab to see these robots and to actually, interact with the team. And, I noticed that they're so humanoid robots are so attractive to look at that when students come, they just can't take their eyes off it. And, we decided to use this idea to actually do some therapy for children with autism. Right, so for autistic children are the one who actually have difficulty concentrating on one thing or actually to keep their focus on one particular object. And what we did is that we actually use these robots to actually give certain stimuli to the child who's actually standing in front of the robot. So we first conducted a series of 6 tests in which we actually got the robot and the child to play soccer with each other. But with time, we realized that for people with severe level of autism, we need simpler interfaces. So we designed a 3-step interface in which first we do involvement, like the child is standing in front of the robot and the robot does some actions in which we see whether the child is able to focus towards the robot or not. So we see the eye gaze detachment and also based on proximity and the engagement duration. So we do that with the robot standing in front of the child. So with the joint, we focus on the joint attention part. And the second thing we do is that now if the child is responding well with the eye gaze attachment and looking at the robot for continuously for a long time, we get the child to mimic the behavior of the robot. Whatever the robot is doing, we encourage the child, the helper encourages the child to actually mimic that motion. And the third one is, of course, the interaction part like soccer, which is for people with lesser severity of autism. These are some of the experiments. We blurred out the faces, and as it was required by our agreement with the children and the Autism Research Center, we've tested this this algorithm in 2 different centers in Pakistan. And this has taken more than 8 months of tests with hundreds of experiments on children. And we are very happy to share that we've done some papers on this as well. So statistical results are there, and it actually resulted in a lot of benefit for the students, because with human therapists, children are used to seeing humans all the time, but robots, they don't see around all the time. So they're really attracted toward the robot, and particularly the small ones like this, which look like a toy, are really attractive for the children. So these are just some plots of some stimuli, and we've got joint attention measurement, joint improvement, sensitivity towards the stimuli, cognitive state of the. We also measured the brain state before and after the intervention. So based on that, we could actually tell. And there are different kinds of, there are even auditory stimuli. Like, for example, you might have noticed in one of the videos in the last slide that the child suddenly moves back. So the reason why he's moving back is that the robot asked him to move back. The robot said that let's take a step back, and the child, interprets that and takes a step back. So we see how much he responds to visual stimuli and how much he's responding to the auditory stimuli as well. We've also, in collaboration with Air University in Islamabad, we've developed this functional near-infrared spectroscopy interface, which is the first of its kind in Pakistan. I think Dr. Umar Asghar will later on be touching on this as we work together on this interface. I think like I've already taken too much time, so I'll sum up things here. And thank you very much for a very patient hearing. And I think some of these projects were interesting. Thank you very much. And if you want to connect with me, you can connect with me on, of course, using my email as well, but I'm there on Facebook and Instagram as well. So for students who are listening, you can connect with me on Facebook and Insta too. Thank you.
Thank you so much. Yeah, thank you so much, Dr. Yasser. Now, I would like to invite our second keynote speaker, Professor Kosuge from Tohoku University, Japan. He will be giving us an insightful talk on robotics and system integration. For those who just joined, Dr. Kosuge is the director of Center for Transformative AI and Robotics, and he's a specially appointed professor at Graduate School of Engineering, Tohoku. Over to you, sir.
Okay, thank you very much. Could you hear me? I'm Kazuhiro Kosuge, currently the director of the Center for Transformative AI and Robotics, special appointed professor at Tohoku University. And also I'm staying in Hong Kong now as a deputy managing director, Center for Transformative Garment Production, Hong Kong Science Park and Hong Kong. Okay, I'm probably will have another position in the University of Hong Kong, but still need approval from the immigration office. So that is my current situation. Today's talk is relating to the robotics as a systems integration. Let me start with my research in the past. Okay, when just after I started robotics research, I had been interested in the cooperation of humans for handling an object. So first, we are interested in how to coordinate two arms, okay? And we have developed about 30 years ago, we have developed a single master multi-teleoperator systems. And this is the original title, but now we should not use this word. So maybe multi-teleoperated manipulator systems would be a nice word. And there was some secret, but fortunately, at that time, computer system was very slow. But fortunately, together, I mean, by the help of my friend working in Sony, we could develop a quite fast computer system, and with which we can realize diorama coordination. So I think this is one of the most early days diorama coordination using industrial robots. And after that, I mean, as an application of robot, these are, I mean, coordinated motion control manipulators. I just thought maybe we can put these robots on a mobile base. Then what I can do? Okay, let me skip this part. Then first I put a 7 degrees of freedom manipulator on the top of the this omnidirectional mobile base. Using that, we could realize kind of a redundant motion. Of course, sorry, this motion. Only one is moving. Sorry, wait a minute, please. I hope. Okay, wait a minute, please. Something is strange. Wait a minute, please. By somehow, it's very strange. Oop. Oh, this is the next slide. Okay, I extended it to the dual manipulator systems. Now, two dual mobile dual manipulators are in coordination for handling single objects. This was carried out about almost 20 years ago. Okay, and then one day I was interested in, I mean, up to now, up to this point, most of my research has been heavily supported by the government. So we apply some research like National Science Foundation research in the United States. It is called granting aid for scientific research in Japan. And but after that, I started to thought that maybe we may want to apply such a concept to some field. Then one of the alumnus of our university visited our laboratory one day, and he's coming from the company who is a kind of an expert of mechanical parking system. And we had a lot of discussions, and you may not know exactly, how it works. In Japan and some Asian countries, since that our parking space is quite limited, we have such a very complicated mechanical parking system. And actually, this is a parking tower. So in order to park your car, you have to precisely place your car on the pallet of this system. And now Japanese are now that we're aging, our country is very, actually the global aging phenomena is really, really serious. Once you get to, you reach to a certain level of age, sometimes you couldn't maneuver your car so precisely. So we came to the conclusion that maybe this system works. Okay, we call it iCard. Once we park a car in a space and we leave the car, then the robot is coming out and grab it and bring it into the space, instead of us. So we thought that this was very, very useful, and we seriously did some development. After several prototypes, this is one again that the prototype. We collaborate with the company. The company was so excited, and we developed this system. Okay, and then, okay, up to this point, the company's CEO was so excited about this project. So he was, he was very, very supportive for our project, and he told us that this could not be used for the parking system, but he likes this concept, and he suggested us to continue this research. But he told us that maybe the robot is too big. Okay, the robot can bring the car into a specified place. Then again, that we become very serious. We developed a smaller car, and this you can see that actually these robots are designed by our students, and we did some experiments using the real vehicle. So we thought that we are expecting that the company is going to commercialize this system. But unfortunately, the company's CEO has been replaced with another guy, and next CEO does not like this concept. He stopped our project. We were so shocked. And actually this works very well, right? And so we were so shocked. Another shocking, things happens. About maybe this is about 5 or 6 years ago, I found these videos on the website. This is called Server, a company in Germany, I guess. Now they have a in Düsseldorf airport. This is before the pandemic. I don't know whether they are still continuing the let us say, operation or not. But I was so shocked because the concepts are so similar. Okay, this lady parked her car and in a designated space and just leave the car. Then the robot is coming. This called the array of a server and grab the vehicle like ours. Of course, the design is different. And when this lady came back to the airport, and then that after going through the gate, getting out of the gate, she let the system know that she was coming back, and then the robot is going to bring the car. And when she arrives at this place, parking space, the vehicle is there. I mean, you can just drive the vehicle without changing its direction. So this was really what we are expecting, but nothing happened. And so what is this? And around 2009, inside of Japan, we have an organization called the Japan Science and Technology Agency. I was a selected fellow of a Center for Research and Development Strategies. We had a workshop and relating to the robotics technology. And at that time, many people are frustrated because up to that point, Japanese government has spent a lot of money for development of new types of robots, but nothing happens. So we were asked to unveil the relation between the robotics research and the social values, societal values, how the research in robotics could contribute to the society. So after a lot of discussions with among the robotics researchers in Japan, one conclusion which we had is that robotics technology or foundations could contribute to the society or could realize societal values by providing services necessary for our society. Okay, and of course, a lot of discussions are made, and yes, this I'm going to skip it. And what's happened? Okay, what is interesting that we have a lot of discussions concerned with how robotics research is going to lead the new services. Suppose that we'd like to develop an elderly care robot. Okay, what we are trying to do is to try to, collect existing technologies usually, like what kind of actuators we have, what kind of CPUs we are going to make, and something like that. But that is not the exact process, okay? What we have to do first is to design and identify a service or services necessary for the application as a sustainable business. Without being a sustainable business, without a sustainable business model, we couldn't integrate the robots, which we are trying to create into our society. So this is very, very important. But I'm not sure. I'm not sure whether this is a part of this is what we can do. Researchers could do or not. Okay. Then, if we have a service model, then we can design a robot system architecture for the service or services with necessary unit technologies. And of course, sometimes we may not have the technology necessary for some robots. So in order to do so, in order to develop a robot, this portion, we have to develop new fundamentals necessary for the service or services. Or we need to develop a new unit technology necessary for the service and services. And sometimes existing technology may not be enough. So in that case, we need to enhance existing unit technologies to meet the requirements of this service for the service or services. And after that, of course, by integrating the Unity technologies together, we can create a robot. And by this way, I'm sure that we can enrich robotics foundations through application-oriented research. As I mentioned, I'm not sure about this, this colored, pink colored portion. We are not sure if we should do that, but without this model, we couldn't develop a real system, okay? Red part is, relatively easily done, okay? Because once that some necessary services are given, we can design a robot system architecture, and we can develop necessary technologies for that, and we can integrate the Unity technology, like in my previous case. Okay, I have done a lot of research relating to the human robot interaction. This is one of the my early days experiments using industrial robots to augment human power. At the time, I was interested in how to augment human power without having any stability problem. We solved it by designing a kind of a impedance-like controller for this system. And I also had an opportunity, I had an idea to try to replace one of the robots, multiple robots, with a human, okay? So in this case, the human is a leader, and the robot is a follower or supporter of this leader, okay? When I carried out this experiment, the late George Giraud, he's a very distinguished robotics researcher in France, and unfortunately he passed away several years ago. He likes this concept very much. He put the photo on the back of his book. So at the time we are so excited. And we developed a mobile robot helper, Mr. Helper, or distributed robot helpers, or Dr. Helper. This was almost 20 years ago. Time flies. And after that, of course, we carried out a lot of different experiments relating to the human-robot interaction. And we found that even if we can do such a robot, of course, some simple demonstration can be done using these robots. But a simple what we learned is that the simple tasks could be done by these robot helpers. But unfortunately, general tasks could not be done easily, even with the assistive robot systems. Yes, thank you. Oh, sorry. Because the robot does not know how to collaborate with the user, okay? So in order to collaborate the user, the robot has to know the task, what kind of task the guy is using, okay, doing. And the guy's its user's intention, how he or she wants to do, relating to that task. How the user, he or she, wants to be assisted, and so on. Actually, we have to solve, robot has to know a lot of information to help its user. So this came to the idea of dance pattern robot. So we started to develop a dance pattern robot research to develop a mechanism for closer human-robot coordination and interaction. Fortunately, we had an opportunity to give a demonstration of this a bit fancy dance pattern robot, PBDR, during Aichi Expo. It's 16 years ago. Time flies. So using the sensory information, we design, okay, in this case, this is supposed to be a ballroom dance, okay? Partner ballroom dance robot is the name of this robot. In case of the ballroom dance, the male dancer leads the dance, okay? Female dancer, in this case a robot, has to estimate, has to predict which figure is coming next. And based on the predicted figures, estimated figures, by the precise estimation, the lady can what I say, beautifully dance the dance. So we designed the human hidden Markov model based. Sorry, my room is very sensitive. I mean, this is energy conscious, and try to switch off my light whenever I stop moving. Okay. And at the time, this was again at about 16 years ago. So we designed the figure estimator using a hidden Markov model hidden Markov model. And we did our experiments, demonstration during the IT Expo. Fortunately, this attracted a lot of people, and fortunately, successfully entertained the visitors to this some place. I mean, IT Expo. Okay, and after this, I was wondering, what can I do? I mean, this is just. I mean, I thought that this is just, in some sense, of course, this was a research for IT Expo. The goal is to entertain the visitors, and what's that? What's else? So one day I visited the company, automobile company, and I was so shocked because this guy fastened the boat, came to here, and took a tool and parts and fastened it. I mean, attached it to the body, and came back and took another parts and put it attached them on the vehicle's body. So I thought that, I mean, this guy is dancing around the body, and then that we can introduce the concept of dance pattern robot. Okay, so if a robot could provide a worker with necessary parts and tools when he or she needs them, the worker could concentrate on the assembly task. That is what we guessed. So we developed a PADI, in-time parts and tools delivery to you robot, and to reduce the worker's load, to improve the efficiency of the work, and to prevent the mistakes of the work, and so on. And of course, similar to the previous dance pattern robot case, the robot has to know a lot of things: the task, its user's intention, how the user wants to be assisted, and so on. Okay, so we developed a prototype system, and okay, and as I brought it to the company, okay, and this is just after the Lehman shock, and they were not so busy. They gave us space, I mean, to check the effectiveness of this proposed system. Okay, so actually he was a very trained worker, and but he is not allowed to attach the parts, because parts have to be attached, I mean, based on the regular I mean, process. But at any rate, by introducing this robot, we found about 20 to 30% of time time required for putting these parts to the vehicle body could be reduced by introducing this robot. And okay, and the company finally agreed to develop a real system. And of course, based on the discussions, we modified the a control system used for the robots. Now this robot, I mean, moved together with a worker so as to minimize the time to pick up new next parts. Okay, and but unfortunately, this is a kind of parts feeding system which was developed by the company. And but unfortunately, 3 months later, they removed this system. I asked them the reason why. I mean, they didn't want to use the robot. The answer is they are very busy, and they did not have, at the time, they did not have enough number of engineers who can adjust the system to the modified process. Okay, in the automotive company, they changed the production system many times. So in order to utilize it, they have to modify the how many parts are attached to the body during one process. So we decided to develop an adaptive motion planner based on the recent development of our machine learning scheme. So now the system, okay, let me skip it. Okay, for the worker's motion predictor, we use the Gaussian mixture model and Gaussian regression model, okay? And the detail is written in this a paper. And for the motion planning, of course, I mean, everything is stochastic in some sense, not static, stochastic, because I mean, worker couldn't continue the same motion every time. So they differ from the nominal motion. So, and in order to plan the motion in a safely manner, and in order to, I mean, we designed the model predictive controller for this system. So the cost function which utilized consists of 3 terms. One is minimizing delivery time delay and the collision avoidance. And the third term is mechanical limitations like velocity limit or acceleration limit. And based on that, okay, we did some experiments. And this is I mean, after the 10th trial, you can see that this is a predicted motion. And after the 10th, about the 10th trial, this robot can deliver the parts to him without any delay. Okay, let me, another one. This is the left-hand side, the first trial means without estimation. And after the one trial was finished, then the, learning is activated. And so after 10 times, you can see that the robot can move much faster, and his waiting time is much smaller. It's the same, okay? And we did, and sometimes they try to cheat the robot, okay? So even if, I mean, he did something strange, he behaved differently from the usual, the robot can provide him parts without serious time delay. Okay, now I think I have to. Now, I mean, the company is interested in this system very much. We are developing a different system, okay? This is our experiment carried out in our university, Tohoku University. We brought a body, and actually white body, not a white body, but a real vehicle's body, and we developed this system. So I hope that we already submitted the patent. So this is now patent pending. I really hope that, I mean, we can unveil the detailed information of this system later. Okay, as a conclusion, I think that many researchers have been interested in scientific issues relating to robotics, assuming that solving the issues will lead to the future advanced robots. Of course, that is true, okay? But we couldn't unlock the potential robotics as it is without knowing the real issues relating to the robot, which we really want to create. So I believe that, I mean, through this technical committees and activities, we'd like to put more emphasis on finding real issues relating to the robot, which you have in mind. When you found a real issue and when you found a good business model, then your robot will be sustainable as a business. Thank you very much for your kind attention. And I think my time has gone. That's the 5 seconds over. Thank you very much.
Thank you, Professor Kusuge, for great and insightful talk. Before we move to our next speaker, we have a little announcement. If you have any questions, please write them in the chat box. We will be happy to address them. Now I would like to invite Dr. Wajahat Mahmood Fazi from Concept University, Lahore. The title of his talk is NIHA, an agent-oriented approach to cognitive robots. Over to you, sir.
Thank you.
Am I audible to you guys? And can you see my screen over here?
Yes, sir.
Thank you. So I'm Wajahat Mahmood Qazi from Comsets. So I'll be discussing Neha. It's a project which we are developing for last couple of years. It was started as a scientific curiosity, but recently we have collaborated with a number of industry partners, and now we are trying to develop its industrial version for an e-commerce company. So I'll be sharing my experience, what we have learned so far, while developing cognitive robots using agent-oriented approaches. So our interest started like 10, 12 years back with the idea of consciousness. We have been observing that, okay, machines are doing very much fine when they learn, when they perform some tasks. But the question is this, that are they really aware of it, that what they are really doing? Or can they really, have this sense of awareness that, okay, fine, I'm a robot and I'm picking an object and I'm going to hand over this object to my human partner. So does that machine has that realization, or it's just merely a mechanical activity and we're just labeling it as, okay, fine, it's intelligent, or it's like the illusion of intelligence? So that question scientifically, hit our mind, and we started investigating that how to make machines conscious and make them aware. And still, frankly speaking, we don't have the right answer to this question. But what we have learned so far is that consciousness is something which we can categorize for machines into two levels. First level is quite simple, as we are doing in AI nowadays, which is more like sensory consciousness. Okay, fine, a machine can like develop some percepts out of its environment through a number of sensors. But the tough job is this, that to develop the idea of phenomenal consciousness, like as human beings, sometimes the sensory inputs are missing, and with those missing information, yet we are able to formulate a construction, a comprehension, and understanding. So how to do it? So while digging into the literature, we came into more weird concepts like quantum mechanics, classical physics, the idea of subjectivity, and personal semantics. So what we learned that without these 5 or 4 components, we might not be able to achieve phenomenal consciousness. Okay, so how to do it? So back to the basics, and then we started looking into from scientific point of view. That first thing is this, that what is the greater challenge when we're talking about consciousness? So we found that there are 2 levels that a machine must, or system must be, whether it's a human system, a living system, or it's an artificial system. When we're claiming that it possesses a certain level of consciousness, then it must be able to depict, imagine, dream, and to construct that phenomenal level. Okay, fine. From scientific point of view, yes, it is very exciting, problem to solve. Does it really going to have some additional applications or not? So when we started, it was more like a scientific curiosity, but recently we have shifted towards more towards its industrial applications. So Neha is technically a conscious agent based on the cognitive elements. So the paradigm which we are using to achieve this consciousness is based on ethics, knowledge, industrial applications, ICT products, using robotics and traditional AI methods, all coupled together in such a way that we are bringing few concepts from quantum mechanics, which I'll be demonstrating later in my slides. Some concepts from AGI, which is artificial general intelligence, which is still a debatable topic in AI community, that whether we can achieve general intelligence or not. But we have just taken few theoretical concepts from this domain. And obviously, we'll be needing a body-like structure. For that, we are using virtual agents and robotics, for that matter of fact. The first thing, or the first matter of the business was this, to have a cognitive model or the architecture which could actually provides all, at least at a theoretical level, all ingredients. So from that point of view, we'll be needing a sensory memory, a long-term memory component, something called metacognitive components, something to synchronize all these components into a framework. So we added a circadian clock, which was an inspiration from human anatomy. And all these things all together must be coupled into a workspace and to organize all these things, because as we are moving on, we'll be adding more and more algorithms on top of this architecture. So the challenge was this thing, that how to add a new component to the architecture while the architecture is running. So we borrow a concept which is called codelets, and we try to to develop all these features like language understanding, vision, learning, sensory models, circadian clock, and all those things features into these codelets things which are running on top of this architecture. So it's more like it's a perfect example of an agent-oriented architecture over here. So from body point of view, we collaborated with NAS, with Services Syndicate, with University of South Asia, and ComSets is obviously over there. So we collaborated with these institutions for robotic interfaces. So we developed our own virtual agent. We are collaborating with NAS for by integrating Now Robot with Services Syndicate for integration of UR5 robot, which is one of the industrial robotics. So where are we standing right now? So in this architecture, the long-term memory is consisting of approximately 14,73,208 nodes of based on knowledge graphs, and approximately 31 lakh plus minus relationships in this graphs. So what we have achieved so far at a function level is a bottom-up and top-down attention. Situational awareness, I'll be discussing what do we mean by situational awareness over here. Semantic sentimental analysis based on emotions, drives and motivation over here, because drives and motivations are very vital and crucial component when it comes to the modeling of conscious systems in terms of cognitive models, imaginations, and so on. So from sensory point of view, the standard activity recognition and those intent modeling are obviously over there. And from action point of view, we are right now sticking with the basic actions like action-specific grasp, pick and place, and all those emotion-like behaviors. So our more primary focus is on these components at this time, which is the cognitive part of the system. A snapshot of the internal knowledge base of which is around the word brain. So in terms of situational awareness, we are trying to model 3 levels of situational awareness in NEHA, which is like short-term, long-term, and long-term situational awareness. So short-term is more like situational assessment of the current scenario based on these sensory modalities. Strategic is something which is like making the wholesome idea that what's really happening in the environment at this time based on the previous sensory cues, which is more like a long-term scenario. Then there is more like analytical aspect, which has some scientific grounding. So these are the three levels. So what we did so far is that we started with the designing of a simple chatbot, because we have to start building systems with simpler ideas or examples. So a simple chatbot is like, okay, fine, what are you doing right now? I'm communicating with you. So that was, but our idea was this thing, that what if we narrate a story to our chatbot, which in this case is Neha, what would be the responses? Like a story, something like this, that today is Christmas, Mrs. Wilson is very happy, she is going to sister house, and so forth. And we start queuing about where Mrs. Wilson is going, what is the event today, and so on and so forth. So would Neha be able to, relate the context and then share share its ideology and the responses based on the story which we have already shared with Neha. So for this, we benchmark, the existing systems like Cleverbot, Mexico, and Alice. So Alice is the chatbot which actually won Lerner Prize in 2015 and 14. So these were the results when we shared the same story with these, bots. So when we asked Cleverbot where Mrs. Wilson was going, so the Cleverbot responded, "I'm going to eat and text you later." Mexico responded, "In the universe that we live in," and Alice was something like this, a place we call reality. So you can see that these are the responses. So this is not the problem with the programming or the limitation of these bots. It's more like they were missing the right ingredients, like the memory systems, the idea of that situational awareness. So when we model these things with into Neha based on that knowledge graph and all those things, so these were the responses from Neha that Mrs. Wilson was doing to sister's house, where she was standing. Mrs. Wilson was standing at the side of the road. And the last question was really interesting, which we were not expecting to get the right response. That who is the person I just told you about? So the response was Mrs. Wilson. So the idea of the subject and object is over there right now. So when we were able to do it, then the idea was this thing, okay, bring into the traditional machine vision systems, because that was the primary building blocks for activity recognition. So pretty much a lot of work has already been done over here. So we just borrowed the idea from YOLO darknet models, and we trained our activity recognition system, something like this. So this is one of the activity recognition system which we have actually trained for Neha. So Neha is right now having the idea that there are 7 types of various activities which through those visual sensory cues Neha can understand what's really happening in the environment. So as I mentioned, that it's just a kind of a building block which was required to build next units of the cognitive domain. So what's really happening over here? It's stuck. Okay, next thing was the idea of affordance. So this is pretty much the point over here. That what do we mean by affordance and grounding? Because when a machine or a robot is going to interact with the environment, the robot must have the understanding that what is the cause and effect based on the properties of that object. So if I'm going to pick a circular object from the edge, there's a likelihood that that ball will slip. So that is the effect of the grasp which was made by the robot from at a certain point. So for this, the machine must be able to understand the semantics based on the perception to generate the grounding and the affordance of the objects to understand that what is the cause and effect. So for that purpose, we actually we built our own data set for these drive models, and we ran some experiments. So I'll share the results with you guys later on. So once that was done, the next part was this thing, that to understand that in order to localize the object with reference to the person who is actually interacting with the robot. So these are pretty much standard computer vision systems. So these 3 blocks were able to give us the necessary percepts for our cognitive unit to develop phenomenal consciousness, which is coming right now. So as we can see that these are the perceptual semantics, that there's a cup and the cup is referred to as a drinkable object. So once the cup is referred to as a drinkable object, based on that knowledge base, which I've already shown in the previous slide, where we were saying that there are more than 14 lakh knowledge nodes over there. So it can relate with those knowledge nodes and understand that what kind of object it is like, seen based on its semantics, based on that knowledge representation scheme. So once this was done, so we coupled the entire thing, and this was our first experiment when we asked Neha to fetch me a glass of water. So in order to fetch the glass of the water, the machine needs to understand something like this, that where it is standing right now. So the entire task planning, the emotion planning, the understanding of the environment, localization of the object, grasping of the object, entirely it was done by this. So we have used a virtual interface with UR5. So yes, the top grasp was something which was pre-planned or pre-programmed. So the idea that in order to fetch a glass of water, the machine must be able to understand that there should be a glass over there. There must be a dispenser. So in the environment, are there those objects available that would be required to complete the task? So once that was done, the entire task planning and the execution is done autonomously. So once this was done, we said, okay, fine. So far we have achieved a sensory consciousness or sensory awareness based on the knowledge base, just on the knowledge base, which is pretty much the easy problem of the domain. Now, how about if we refer, I'm feeling thirsty? So I'm not directly asking that give me a glass of water or something like that. I'm just referring my internal state. So would it be possible for a machine to understand that if the person is feeling thirsty, so there's an implicit need or want over there, and how I'm going to fulfill that need and want? So for that purpose, we started developing the imagination block. The first thing was this, to make Neha understand that based on the lingual cues, will it be able to construct the simulated environment? So this is what happened for motion planning. So this is the real world environment, for example, and we are using Gotham for motion planning. The first thing was this, that in order to run the entire situation or imagination in the simulation world, we need to construct the same environment in the Gotham at one time. So we use RASNet and darkened models to construct the real scenario into the simulated scenarios. The results are in front of you. So once that was done, so this is the paper which we published for this one, and these are the results. So over here, Tanvi, one of my students, is asking Neha that I'm feeling thirsty. So these are the results. So there are so many options in front of you. The back of the screen, you can see that the entire real world was constructed at one time by Neha based on that perception thing using RASNet and other models. So I'm feeling thirsty. This is the result. So over there is a Kokomo and snacks and all those things. So over here, the Neha actually identified that there is the element or sense of want over here. So I must get myself aware to fetch something which is more likely associated with the drinkable thing. Over here, the idea of affordance and then the grounding came into play, and it evaluated on the basis of the semantics, grounding, and affordance, that which of these objects are most likely the one who are going to fulfill the first element. So the next part was this thing. Okay, fine. All graphs were the top graphs. So as we all come from the robotics community, you know that most of the time top graphs are the valid graphs. But when it comes to the action-oriented graph, maybe if we want to serve a glass of water to our guest, so top gas is something which is not appropriate, or it's acceptable. It should be from bottom. So in this case, from the set of the valid gas, we need to further filter out based on the action, that which gas is the valid one. So this is something which we have used in collaboration with University of Polytech Catalonia. So this is the paper which we have recently published in ETFA. Over here, we are trying to use various neural network models based on graph data set to train our machine to learn to grasp based on the action. So we have not yet integrated with the Neha right now, but this is something which we are working right now at this time. So coming to the part of the dream, once we were able to construct all those things, we actually modeled quantum neural networks and quantum genetic algorithms to develop an AI in model, which was published in 2009 in the library report. So this is something which we got. It's a 10-second level 1 dream. So there are 5 levels of dream. This is one of the first level of the dream which we were able to model based on that 10-second sleep unit. So from these things, then the next part or the basic ingredient was the ethics. So right now we are working on this ethical part also, based on cognitive models. Like we have actually modeled the entire psychophysiological pathway of humans into a simple environment where we are actually modeling glucose, insulin, sodium levels to see that fine, and the physiological aspect of these things. The machine is its own goal based on its current emotional and physiological states. Like emotion is now hunger because all these parameters are in a very bad position, and so on and so forth. So once this was done, so we thought about okay, fine. If the state is very bad, so what kind of rules, ethical rules, it is with the Holy One, and we did out all those ethical parameters. My student Sadapa was there at that time, so she did a lot of effort, and we extracted more than 100, ethical models from there. Right now, we are trying to model these parameters in Neha. So this is the knowledge graph of those ethical parameters, which is something which we are working on right now. So what we have done so far is that we have used that model and reinforcement learning to execute a self-driving car model. So these are the it's something which we are working right now on ethical grounds. So I can skip this one, and these are the consciousness analysis between working memory and long-term memory. So according to Comscale and quantum misinformation theories, when the spikes are above 0.5, at that moment the system is aware of its environment. So when the information was being transferred between working memory and the long-term memory in the workspace, we can see that there are a number of times where the architecture was having conscious activity within its life, as we humans do. And when the contents were transferred between sensory memory and which suggests that there was no conscious activity which Neha was able to register or was able to get aware of it. So can we claim that it is conscious? No, we can't claim at this time, because according to Comscale chart, there are 11 levels for system to become conscious. So the state of the art, which is right now, is LiDAR model, which is right now at level 4. So Neha is at level 3.5 something. So we still have to go a long way to make that claims. So I was referring that recently in January 2021, we met a guy in a company called Ecologics. This is a US-based company which they are working on, eBay and all those things. They have their own warehouses and stuff like that. So I shared my presentation of this Neha with them, and this company really got very interested and excited with the results. So they asked me to convert the entire system for their e-commerce system. So we are now revamping with the Neha for their warehouses, for their robotic inventory, and for all those things based on these three components. So they have provided their own cognitive infrastructure, and the timeline is for next 5 years to integrate e-commerce intelligence in terms of process automation, cognitive insight, and cognitive engagement. So what we have so far achieved for them, these are various architectural layouts which they have provided. So we have right now we have been able to convert entire RAS integration, because they are working their in-house, hardware and required machineries for their warehouse systems, which will be integrated with RAS recently in future. So this is something which we have been, done so far in 6 months, that we are able to revamp the architecture for their need. We have been able to predict, what kind of, searches will be in the market based on hierarchical temporal memory model, because they are dealing with a number of, refurbished items. They are actually dealing with 50,000 plus items. So we started with the laptops and computer items. So we are able to right now classify damaged with on-screen, off-screen, and all those things integrated with their internal firmware and all those assembly lines. So this is how now we are putting Neha from academic research to the industrial research. Thank you very much. This is all from my side. So. Any question? I'm not sure that yeah, it was about time.
So do we have any question? Dr. Wajahat, are you here?
Yep. Yes. I'm here.
Okay. Are you done with the presentation?
Yes.
Okay. Thank you so much, Dr. Wajahat. For those who just joined, a recorded version of this workshop will be available on our Facebook page, and I'll also be sharing the link of our Facebook Live in the chat box. So before moving towards our fourth speaker of the day, we will be having a short 15 minutes break. So stay with us, and meanwhile, please visit our page and like our Facebook page. Hello, everyone, and welcome back. So welcome back to our workshop on intelligent robots for practical application, jointly organized by IEEE International Technical Committee of Robotic Research for Practicality in collaboration with IEEE RAS Pakistan and National Center of Artificial Intelligence. Now we have our fourth speaker with us, Professor Dikai Liu from University of Technology, Sydney, Australia. The title of his talk is Field Robotics and its Application in Civil Infrastructure Maintenance. Over to you, Professor Dikai.
Thank you very much. So can you hear me?
Yeah.
Okay, thank you. That's great. Yeah. Thank you very much. This is my great pleasure to talk about robotics research for civil infrastructure maintenance. So there's so many different types of civil infrastructures, like bridges. We have so many number of bridges in the world, like 42,000 bridges in Europe and 210,000 bridges in the US and many 100,000 bridges in Japan. Port is another civil infrastructure, which is very big in the world and very just big industry in the world as well. Towers, like the transmission towers, which you can see in the field, and also pipes, the underground water pipes and sewer pipes and the oil and gas pipes, all of them are civil infrastructures. Underwater structure, like the bridge piles, or like the underwater pipes, and those pipes and these structures require regular maintenance as well. And oil and gas is the offshore platform, and also the stations. You can see here a lot of civil infrastructures. Maintaining this infrastructure is very difficult and very challenging. Here is one example. You can see this video shows two people there doing sandblasting or abrasive blasting to remove the old paint and the rust from steel structure like steel bridge. It's very noisy and a very dusty environment, and the operator has to support a big reactive force from the nozzle, could be more than 100 newtons. So it's a very difficult environment. So this is about bridge maintenance. And also because of the high pressure grit or abrasive material, and it's very dusty and it's very risky to people. Inspection of civil infrastructure as well, you can see here, people doing the inspection of bridges. You can see the pose of the inspector is very dangerous. This one shows people have to inspect the confined space, which is even more serious in terms of safety, because if there is anything goes wrong, then people will not be able to rescue them. And you can see another example here is so difficult for people to do the inspection of the bridges. So transmission tower, which is another example of civil infrastructure in the whole world. People are still climbing the transmission tower, doing the inspection, cleaning, and painting. So, but it's so difficult working on heights, and also, if they have to shut down the power, otherwise it's so dangerous for people. Underwater structure, like the bridge piles and the water, the wharf piles, they have to use the high pressure water to remove the marine growth before they're doing the painting or before they're doing the inspection. So you can see here, the divers have to do the job, but they are working in a very difficult situation, very difficult environment here. Unfortunately, this is the whole situation in the whole world. Divers are doing this kind of tasks. So then we have so many critical issues here. For example, the environment is hostile and hazardous, and also it's labor intensive, particularly for the blasting. They have the paint, which may have lead or asbestos as well, it's very difficult to access some areas in the infrastructure and all can hide as well. The cost is very high and the productivity is very low. So what is the promising solution? And we think a robot can provide a very good solution, which is what we call the robotic co-labor, to help people for the maintenance of various civil infrastructures. But in order to have robots to work in such kind of very complex environment like this one, like this one, like this one, is very so challenging because the robot has to operate in unstructured environment, very complex structure environment, cluttered, knowing or unknowing from the robot point of view. Because there's in many bridge structures, for example, they don't have kite joints, or if they do, the kite joints are not accurate. So the environment may change as well. For example, if there are many people around in the environment, which means the environment is changing. And also for the underwater environment, they have strong current. So the robot may have to collaborate with people. So, but in order for robot to do such kind of jobs, it's very, very challenging. So then we have so many research questions we have to answer. The first question is that how a robot can be physically capable to move around in a very complex structural environment. So, and also has to support itself. So this first question. So in order to address this question, we need new design methodologies. Second question is that the intelligence of the robot. How much intelligence the robot should have in order to do the tasks in such environment. For example, the robot has to be able to sense, has to be able to perceive the environment, has to be able to navigate in the complex environment, localization and building the map. And the robot has to know the environment and it has to be aware of the operation. Motion planning collision avoidance becomes more challenging, particularly in a very complex 3D structural environment. What kind of level of autonomy the robot should have? So remote operation definitely is not going to work, mainly because of the complexity of the environment. So how much the robot should be able to learn from the real operation? So this is the second question about the intelligence. Third question is about collaborative operation with human or other robots. So if the environment is so complex and the robot is not capable enough in terms of intelligence, so in that case, we can put the robots and the people together to do the job by combining the strengths of human with the strength of the robot. So, but in this case, we really need to say, so human and robot has to be able to work together, and the human can just use their capability to handle uncertainty and incomplete information, and the robot can use its strengths like speed, power, accuracy, and repeatability. So those are the three questions I have been trying to answer in the research on intelligent robots for civil infrastructure maintenance. So fully automation, like what we have said in car manufacturing or in the factory, they cannot be used in the field for infrastructure maintenance. So the only other two options we have, as what we discussed here, one is fully autonomous. So we have robots to do the job by themselves, or robots working together with people, or what we call the robotic co-worker. So my research topics here, one is about field robots in unknown and complex structural environment. I have been doing a lot of research in this topic and developing robots that have been deployed in real infrastructure maintenance environment. Second research topic I have been doing here is really physical human-robot collaboration. So we have is a human work together with a robot, or is a human work together with different types of robot. So then basically combine the strengths of human with the strengths of the robot. or many robots working together, like robots moving containers. So those are the 3 research topics I have been doing towards infrastructure maintenance. So today's talk, I will be more focused on robots in unknown and complex structural environments, like bridges. So what I'm going to talk about here, one is about the design methodology. As what I said, for the first question, we need to know how robot can move around and support itself. Second one is about the bio-inspired robotics, sensor perception, localization, and mapping in structural environment, fast real-time planning, and the robotic systems development. So this will be the main topics of my talk today. So first one about the design methodology. For example, if you are going to have a robot which is going to operate in the confined space or in this kind of structure with rivets everywhere, or in this kind of confined space with cross members here, or climbing transmitting towers like this. So it's difficult. What we have done, we have looked at the different way of, or different animals or the insects, and how they climb, and how they avoid collision, and how they get across obstacles. The first one we look at is ants. Originally, we thought ants is very capable of climbing, and also can transfer, you see, from vertical to horizontal, or from horizontal to vertical surfaces, which is true. Then we thought we were trying to get ideas. After a lot of experiment and analysis, we were trying to get ideas. How can we learn from ants and then develop a robot like ants that can be used in real environment like this one? So after a lot of research on ants, and we get a very good understanding on how ants climbs and cross from here to here and transfer from vertical to horizontal surface, then we start to design a robot like ant. But by the end, we didn't go ahead, mainly because the ant is so capable with the legs. But based on the current engineering technologies we have so far, it's so difficult to find motors or actuators to have this kind of capability to support a heavy robot in such environment. So basically, look at ant is a good idea, but in reality, if you want to develop a robot for a demo in the line, moving on the slide, on the flat or smooth surface, that's okay. But if you are going to have a robot in the real bridge, it's so difficult. So second thing we look at is inchworm. You can see this inchworm, it's very capable to move around with different surface. Then we start to develop a robot that just use similar mechanic structure like an inchworm. You can say move around a flat surface, transfer from vertical to horizontal to vertical, then from one vertical to another vertical surface. You can see here, it works very well. But what is the adhesion mechanism? So that is the one we put a lot of effort there. Then third one, we look at birds. Birds do the climbing. It's so capable, with 2 legs and sometimes with the back, and they can just climb this kind of vertical structure or in the inverted way. You can see here, in the inverted way. With this analysis here, and we can say, okay, how about we design a 2-leg or 3-leg robot which can climb this kind of structure, like this kind of girder. But in reality, theoretically, yes, we can, to develop a robot which can be used to climb a structure, but practically it's so difficult because the robot has to be robust enough to make sure it is safe. You can see the bird here, they use the mouse or the pig to hold on as a third leg. So definitely 2-leg robot can do the climbing, but it's really, really unstable. 3-leg robot can do the climbing as well, but it is difficult, particularly if you want to have a guaranteed safety. So then we thought, okay, this may not be a good idea. So then we look at how people do the climbing. Like you can see here, when people just climb a structure like the transmission tower here, and how people make a decision, and how people do the climbing in terms of the posts, in terms of the selection of the beam members in the tower, and also we look at how people just doing the rock climbing, and then we analyze the motion, analyze how people did the decision making in terms of the selection of the beams, in terms of the posts, in terms of the use of hands, in terms of the force required. So then we start to, based on this analysis, then we start to develop a robot. So I will show you some examples later on from what we have learned from biological systems for the design of the robot. The second topic we look at is about sense and perception. Particularly if you have a robot in such environment, the robot does not know the environment before the robot gets into the environment. So which means the environment is unknown to the robot. So the robot has to use its sensor to sense the environment, to build the knowledge of the environment before the robot can do anything. So this is what we call the sense and perception. So, and you can see here, we just implemented the algorithms with different platforms. So this robot is doing the inspection, doing the exploration of this environment. And we have the I-beams, we have the rules. They use the sensor information to build the 3D map. Again, this robot is a very small robot in the bridge structure, and use the sensor to collect information of the environment, and then build the 3D map. So again, this is about sensor and perception. Then, based on sensor information, we have to build a very detailed map of the environment. For example, if you have a structure like this, we need to know the surface, we need to know the normal of each surface, we need to know the angle, because otherwise the robot will not be able to act. Will not be able to act, or for example, to do the cleaning, to do the painting, if the robot does not know very accurately of the environment. So to get the accuracy is another challenge. If we want to use the common available cheap sensors, but if you are going to go for very expensive sensors, then it may not be feasible either. So you can see here, this is the robot doing the localization and mapping in the bridge structure in a confined space, then building the map, and then this is another robot, legged robot with 4 legs here. You can see here. And the robot uses the LiDAR sensor here to sense the environment, and before the robot can start to move with its 4 legs here. And this is the similar environment to this real bridge structure. You can see this robot just right now is using the front leg. But because the robot is heavy, there is a side problem. They have to put the toes onto the space between the rivers. So again, this is a challenge. So we have to make sure the robot get very complete and accurate information of where the rivers are, find the gaps, and then control the robot to put the toes to the gaps between the rivers. So this is the localization one. For underwater 3D mapping, and you can see here, this is the robot in the underwater environment, and which is going to clean the bridge. And before that, the robot has to use the sensor to build the 3D map of the surface of the bridge pile and identify the marine growth before the robot starts to do the cleaning. So you can say this is basically a very typical slime problem. But in underwater environment, slime is challenging because of the visibility, because of the water current. So it's very challenging. So then very fast or adaptive real-time planning, you can see here, this is the simulation and this is the real robot just moving in different steps. So like flipping over or the shuffling step, then just say attach to the vertical surface. Then this is the manhole here or a small hole here like this one. The robot has to go through the small hole. But before that, the robot has to do a very good planning. Otherwise, the robot will not be able to go through the small hole. So, and here is the experiment we did in the lab. You can see the robot. and they transfer from one surface to other surface, and in this surface, there are many rivers here as well. They get into the other side of the hole. So this is what we have done in the real environment in our life. This is the robot on the bridge, and on the Sydney Harbour Bridge, which is very close to the Opera House. You can see the robot has to move in on the surface with river, and also a lot of RAS around here, and also to the transfer from the bottom to the vertical surface and then move around. You can see how challenging this application is for a robot to do the job. But again, we have a robot probably is the only option to avoid people to be inside the confined space to do this kind of difficult job. So this is the negative robot you can see here, and in the confined space, and again, the robot has to go through a small hole here. So what we design is the robot to make sure the robot has the sensor to collect very accurate information, and then plan its motion and move around and to go through the manhole. There is a manipulator in the front, which we can attach the tools to here to do the cleaning, vacuuming, and the painting. So again, this robot is the one we developed for the confined space inspection. So here again, it's very challenging, and particularly from the localization, mapping, and control point of view. For underwater application, for example, like if you have a bridge here, and the bridge structure, the piers, it's complicated. How can you have a robot, like for example, underwater robot with manipulators here, go through this? So that again, this is about the motion planning approach for the autonomous underwater vehicles in a very complex environment. So we have done a lot of research here, really trying to make this, allow the safe motion of the robot in such environment. Again, if you have many robots working together, so for example, robot 1, robot 2 here, to clean the surface of one plate here, and this is the obstacle here, and how you are going to allocate the area, how you are going to partition the area, and then allocate the smaller areas to robots to achieve the maximum outcome or most efficiency. So this is another research question we have been doing here. So those are the research work I present here. We have been doing in terms of the fundamental robotics research, and then we have applied such robotics research outcomes into the development of many different types of robots. The first one, which is about autonomous robots for surface preparation, and for example, for the maintenance of the steel bridges. This is the Sydney Harbour Bridge, and this is the robot we developed. You can see in this complex structure, the robot, when you press the button, the robot starts to use the sensor to sense the environment and to scan the environment and collect the data and build a 3D map of the environment. You see, this is the mapping stage. Then after the map is built, then the robot uses the information what it has to fine-tune the map, to make the map better. This can say it's difficult because of the complexity of the structure. Then the robot starts to do the planning for cleaning. This is the mock run or simulation. And after that, we just the operator press the button. Then the robot will start to do the blasting. The whole operation is done by the robot. All the decisions are made by the robot itself. And what the operator did, just only monitor how the robot is doing the job. And they don't have to interact with the robot, because this robot is an autonomous robot. And he says this is cleaning of the surface in the roof. Of course, you can have many robots working together. You can say you can have one robot on one side and the other robot on the other side. You can have many robots working together. So this robot has been deployed in the Sydney Harbour Bridge and for maintenance of the bridge, like this one. This is the Sydney Harbour Bridge. Yeah. and which is on the side of the opera house. Second example, which is a climbing robot. And as I mentioned, we studied the inchworm and we designed a robot like the inchworm robot. And this is a robot which we developed and deployed in the Sydney Harbour Bridge for inspection of confined space. And you can see the complexity of the structure. And this is the inside of one arches in the confined space. The robot, you put the robot in, the robot uses sensor to find the safe way to go ahead. If there's a hole, the robot will find the best way to go through the hole. And to do the inspection on the other side, and after the inspection, the robot comes back to the start point. So again, this robot has been deployed in the Harbour Bridge for maintenance of the, for inspection of the confined space in the Harbour Bridge. Then after we developed the robot for the inspection of the confined space, then the company wants to have a robot to do the cleaning of the confined space and do the painting inside the confined space. Then we developed another robot, use the similar kind of core research outcomes, algorithms. You can see the robot, this is simulation, and this shows how the robot moves. This is the mapping in the real bridge structure. This shows the robot does the doing the blasting to remove the old paint and the rust. This shows how the robot does the vacuuming. So again, this is the fully autonomous robot as well. There's no need for people to interact with the robot or to remotely operate the robot. The robot makes decision by itself. So this is another robot here we developed. And what robot? This is the robot we developed for bridge piles and wharf pile cleaning and the inspection. So you can say this is the robot in the tank in our research lab, and this is the robot in the real environment. So you can say this is the robot in the real environment. The robot just move around the pile and then use slime technology to build a 3D map. Then based on 3D map, the robot identifies the surface condition, doing the planning for removing the marine growth, then use high pressure water to remove the marine growth. You can say this is how the robot is removing the marine growth. And after the cleaning, then the robot move again around the pile and collect information, build the map, and then do the inspection. So again, all the decision is made by the robot itself. So, and okay, this is another, I have 1 minute, okay. This is another research work we've been doing with TEPCO, a company in Japan, and we developed robots basically can climb transmission towers for inspection, more for inspection is not important, but more for cleaning and painting. Because in inspection, people can use drones for inspection, and they don't have to use such complicated and very complex robot. They can use drones, which is much easier. But for cleaning and painting, then they have to have a robot there. So this robot is doing good. So I would like to acknowledge many companies who have supported, many funding agencies who have supported this research, including Australian Research Council, Roads and Maritime Services of New South Wales, and many other companies, including TEPCO in Japan. And so those are the robots my research team has developed. And you can see many different robots. For some of the robots you have seen here, but for other robots like this one, and you have not seen here yet, they're still under development. Okay, so this is my talk. Thank you very much.
Thank you, Professor Dekai, for great and insightful talk. Now I would like to invite our second last speaker of this workshop, Dr. Yasir Niaz Khan from University of Lahore. The title of his talk is Citrus Field Surveillance Using Drones. Over to you, sir.
Hi. Thank you for the introduction. I would just share my slides and then we can start. I'm sorry. I hope you can hear me clearly.
Yes, sir. It's visible.
Good, thank you. So my name is Yasir. I am at the University of Lahore in the Department of Computer Science, where we have established a research lab on robotics and IoT. So we have been working on agricultural automation, drones in agriculture, AI in agriculture for a long time. Recently, we did the project about citrus surveillance. Before this, we have been working on wheat fields, rice fields, cotton fields. But recently, we shifted to orchards, orchards as well. So we have done some projects with drones on orchards. One of the uh, most important fruit crop of Pakistan is the citrus. So we started off with citrus projects. So I will briefly talk about this, and then if the time permits, then I will talk about other projects as well. We know that citrus is very important in Pakistan. Pakistan is one of the largest citrus producing countries. We are ranked 13th in the production of citrus fruits, and we have a lot of variety of citrus fruits. Uh, citrus exports have been increasing slightly, but we need to increase production so that we can increase the export as well. 30% of total fruit production in Pakistan is of citrus, different varieties of citrus. So we approached the citrus monitoring problem with two angles: citrus tree management and citrus production. So when we talked to the citrus farmers, citrus growers, they said that they need to monitor the trees as well, because one look at the tree and they can estimate what kind of what yield they would get this year from this tree. So they take into account the colors of the leaves. They take into account the canopy, the spread of the tree, the height of the tree, the branches, and etc. A lot of things. So one thing is to survey the tree, to estimate the health of the tree, and then comes the part where we estimate the citrus production. So when once at the flowering stage, a lot of people go in the citrus farms and they estimate the production that they are going to do. And a lot of farmers also make contracts with the contractors based on the flowering of the trees, which is a very rough estimate. Even after flowering, if they take into account very small citrus fruits, that is also a very rough count. So the idea was to take drones into citrus orchards, and through their surveillance, we try to estimate to come to a much better estimate than these rough methods. There are some existing solutions, but they are either very specific or they are performed in ideal conditions. Could you please mute the mics of other speakers? Thank you. So our solution is that the copter takes off, patrols the citrus orchard, and makes a video. Then the video is converted into images, and deep learning techniques are applied on them. Using this, we estimate the citrus yield, we check the tree health, and we count the citrus trees and citrus fruits. So the platform that we used for this was a drone, the DJI Tallow. We have been using DJI Phantoms and other copters as well. Those have we always got this question that they are very expensive for very small farmers to afford, to be able to afford. So this time we wanted to start with a very cheap drone, DJI Tallow, which is a much cheaper version. We ran into a lot of problems when we operated it outdoors because it does not have as much wind resistance as DJI Phantom drones. But on the other hand, once we are between the trees, then the the gusts of wind, they are cut down by the trees themselves. So if you fly on at a very high height, then we have the problem of wind. Otherwise, if we lower the drone a bit, we can also work in the fly around in the citrus fields using cheap drones as well. So we have three modules which are used here: yield estimation. We use deep learning techniques such as faster RCNN, etc., for the estimation of yield of the citrus orchard. We do the health check, again using deep learning techniques. We do the tree counting with the help of image processing techniques. We will briefly go through them and then work towards other problems. So we use TensorFlow with faster RCNN. We tried different models of deep learning in this problem, and we found out that faster RCNN is good in both in terms of performance and in speed as well. Because while flying a drone, if you want to do real-time processing and make decision based on the processing of the drone video stream, then we need real-time processing as well. Input images are passed to the ConvNet, which returns the feature map for that image. Then we do region proposal network is applied on these feature maps. This returns the object proposals along with their objectness score. And ROI, region of interest pooling layer, is finally applied on these proposals to hone down on the features. So this is the methodology that we applied. Finally, the proposals are passed to a fully connected layer at the end of the deep learning architecture to classify and output the bounding boxes for these objects. So you can pictorially see all the steps that I outlined in the previous slide, that we have the conv layers, the way where we get the feature maps, we have region proposal networks, where we get the proposals, ROI, we do ROI pooling, and then classify. We then the next step is to do yield estimation using digital image processing. We take images of these oranges on the trees and on the plants. And then we apply different morphological operations on them to extract the oranges. We also detect contours, as contours is one of the salient feature that we found out is most useful in detecting oranges. So here we see the pipeline, the deep learning pipeline for yield estimation. We input images to the deep learning model. We do image processing, pre-processing the images, and then after pre-processing, the images are passed to the machine learning phase, where the fruit is detected, and then then it draws a square box around the fruit. Each labeled object is taken as a separate object. Then labeled objects are counted, and then the number of labeled objects are displayed. So this is how we do the fruit counting on every tree. So again, the approach is to let a drone fly around a tree, and then look at the tree from all possible angles, and then we use deep learning to count the fruits from different angles, so that we get the whole fruit count of the whole tree. Actually, an orange tree or a citrus tree has a lot of fruit, even hidden behind the leaves as well. So it's important to go around the trees and get images from different angles, so that we can have a look at the occluded fruits. Here you can see one of the images where we have some fruits which are occluded by leaves as well. And you can also see the confidence level of our classifier, that with each classification classification, it also outputs the confidence level. On a more zoomed out image, we see the whole tree. Well, it's a very small tree, but we see the whole tree, and then we see the citrus, and then the bounding boxes of those citrus and the confidence values. We did a lot of experiments with different trees, 20 different experiments. And here you can see in the first column, what was the count of the oranges in the on the tree. We could see very scarce examples like 1 orange to cluster of oranges like 54 oranges. Then we could see how many oranges our algorithms were able to detect. And mostly when the orange is not detected, the reason is that it is occluded by a lot of leaves. These are the confusion matrices, the confusion matrix for detection. Then we have confusion matrix for counting. And then we also detect the health of the tree. And as I said earlier, that the health of the tree depends upon the colors of the leaves as well. The farmer, when he wants to look at the tree and estimate how good or bad the health of the tree is, a lot of emphasis is put on the leaves of the tree. So here we also did the classification of healthy and unhealthy leaves. Here you see them in the lab conditions, but we also have performed these operations on the drone footage as well. Here is the confusion matrix for healthy and unhealthy prediction. Then finally, tree count. We attain tree count with the help of digital image processing. A few of the main techniques are morphological operations like erosion and dilation. So when we are talking about tree counting, we have to observe the orchard from a distance, so that we can get a lot of trees in the camera, in the viewpoint of the camera. So this is the area where we had most trouble with the telodrone. It was very unstable in the wind, but we still got managed to take a lot of stable pictures with less blurring, and we were able to successfully perform the image processing algorithms. So after erosion and dilation, we do image segmentation, we take contours, and this is the whole pipeline of the steps that we perform: the input image, HSV image to NP image, HSV blur image. Then we do the segmentation image, and you can see the black image as the segmented image. Then we do the grayscale image, and then we after erosion, we get the count of the trees. So the last step is dilation, and then the final image. After all this process, contours are applied, which give us an objects to detect. At the end, all objects are added to give us the final count. So this is our students who have launched this as a service. So this is the website, the interface, the yield estimation page, health check page, the tree count page, etc. So that was about the citrus surveillance, the project specifically. Now I'll talk about different other projects that we have been mostly doing with the industry and also with the academia. Our most recent project is deep learning in cybersecurity, where we have a security firm which provides security solutions the world over. What they wanted to do was to make their solutions intelligent. So they want to put more artificial intelligence, more machine learning into their solutions. So we have been collaborating with them, developing different solutions. So the first step was to ensure login security for their clients. For that, we have to monitor the online activity of the clients, the login procedure, This includes the multi-factor authentication. So all of the factors that are involved are checked, and they are monitored, not only checked, but they are monitored over long periods of time to detect anomalies. So we have this anomaly detection module in them, and based on if we find out an anomaly in the normal procedure of a user, we can immediately at the runtime revoke user access rights. Then we can one of the models of deep learning that was tested on this approach was uh, a model which has sparse encoding. So the idea is to have levels and levels of neurons with a lot of sparse encoding uh, neurons among them. So what is the benefit of sparse encoding? The benefit is that we have a lot of flexibility. So we can we always have neurons which can take on learning. And it has been demonstrated that this type of learning is actually what takes place in human beings. Even if some part of the brain gets damaged, or even there have been experiments where they actually physically where the brain was cut, a small part of the brain was cut out, and it was observed that other parts of the brain took over operations that part was doing. And this is because, at least this is what they theorize, is that this is the reason, because of sparse encoding capability in the human brain. So using that approach, of course, has a lot of extra computation power which is needed, but we can hope to have long-term intelligence using that. So the goal there was to, in less than 10 epochs, we learn the model, we learn the problem, and we make a successful model. This is the behavior that we continuously monitor for the user. In the multi-factor authentication, when we look at multiple factors, one of that factors is face verification and face recognition. So face verification is a problem when we verify whether the person in front of the camera is the legitimate user or not. Then comes the problem of face recognition, which is a larger problem, in that we get a picture and we try to identify which person is this from among thousands of persons or millions of persons. Then there is a problem of spoofing, with a lot of face recognition algorithms and applications out there. In our mobile phones, we have this face recognition ability. There is a lot of chance for spoofing. The simplest form of spoofing is to print a picture of a person and show it to the camera and get the device to be unlocked. So we need to be able to detect that it is not an actual person, but we are showing a picture, no matter how good quality that picture is. And based on, if we suspect that it is a picture, we can we ask the user to either rotate his face or do some expressions or something like that, some movement, which is not possible in static images, but which is possible only with a real user. So we try to identify the real user using this technique. Then there is also the problem of 3D face reconstruction, using as little images as possible. We try to completely reconstruct the 3D face of the user. This is useful in, again, in spoofing detection, but this is also useful in many other applications. Like, we want to create avatars of the users, we want to have visual effects on the user customer's face, like these Instagram filters and something like that. So this is our recent collaboration with the industry that we have. There have been previous collaborations as well. One of the collaboration was one of the largest fertilizer manufacturers in the country. They have a huge plant, built near a gas field, and they run the plant very efficiently, very optimally. But they were wondering whether AI and data science can be used to further optimize the solution. So we took some values of the sensors that were put on by General Electric on the whole plant. We analyzed the values, we cleaned the data, we give it to a machine learning model, an AI model of regression, and then for the first step, we predict the output of the plant in terms of tons of fertilizers produced. And the second step is we do recommendation on the controls of the plant so that the production can be increased without increasing the cost too much. So a lot of people do this mistake when they are designing such a regression system. In the objective function, they put on only positive variables without putting the negative variables. So it is just like how can I increase the production of the plant? Just use more raw material. Just increase the process. But what is the cost of doing that? If we do not put a negative variable in the objective function, the cost is ignored, and the model will recommend to use maximum possible raw material, maximum possible settings to get the maximum possible production without considering the cost benefit ratio. So this is the interface that we designed for them, in which we have some control variables, and we suggest the values of the control variables to get the best cost benefit ratio. Another industry project that we did was with a social media app giant that consists of companies in the Middle East and in Pakistan. So they wanted to make a social media app, Favor, which should be able to compete with Instagram and the likes of it, but it should have advanced AI. So the first thing was to categorize the content uploaded by users and to filter it as well. So what they started off was with Google Vision API, IBM AI Engine, namely Watson, and Microsoft API as well. But none of them worked as good as they needed, because they needed it in their setting, in their environment, whereas these APIs are very general purpose APIs. So in experimentation, we found out that these are good general purpose APIs, but they do not work very good in specific environments. So what we did was we made a custom classifier on top of these APIs, in which 1, 2, or 3 of these APIs could be integrated, and based on the output of these APIs, it would form its own opinion. So even though all of these APIs individually were performing 60 to 70%, our custom, ensemble was able to perform above 90% in this case. So our goal was to do categorization of the content, and it's impossible to predict what kind of content the users will upload. So you have to be open to all kind of content. So when we looked at categorization, we found out that Google somehow suggests up to 80,000 categories. So writing a classifier with 80,000 categories is in itself a challenge. So we started doing that, and aside from that, we also had to design filters. We had to filter adult content, we had to filter violent content, medical images containing bloods and operations, and racist comments. So we had to design one filter for each one of these problems. So this is the output of Google Vision API. If you give it an image, it gives you a lot of labels and its confidence. So looking at these labels and a very long list of labels and their confidences, we have to come up with some integral model where we incorporate these labels, their confidences, and the labels and confidences returned by some other PI. So this was a challenge to write an ensemble classifier for all of these. These are the word embeddings which are there, available, publicly available. The files are in gigabytes. They contains word embeddings, and the benefit is that for every word we get a vector, a numerical vector, and then we can compare the closeness of words like synonyms and antonyms, and based on that we can do a more flexible searching. So glyph also provides these numerical vectors instead of words. So this is the interface that was designed at least for the company, where we have the contents uploaded by users, and then we have the tags that we decided are the most important tags. This is our loosely coupled research group, where we have collaborators at different universities. We have 2 PhD students, we have researchers, graduate students, and undergraduate students. There is a conference, a Park German workshop held every year. Actually, there are 2 versions of it. One is held in Germany, and the other one is held in Pakistan. The one in Germany will be held next month, and but it will be online. And the one organized in Pakistan would be later this year, maybe October and November, and it's not clear whether it will be physical or online. So we have already talked about agriculture. So these the further slides, they contain our work on different aspects of agriculture. So agriculture is very important in Pakistan. It constitutes 25% of Pakistan's total land area, 19% of contribution to GDP, and employs 42% of labor force. Cotton alone accounts for 46% exports of the country and employs 35% of labor force. So these are the important crops, and we have been. Since I have only 2 minutes, so I'll skip to the further part. The basic idea. We started off with drones. Like I said, the parrot drones, the DJI drones, the phantom drones. These drones are becoming more expensive. There is always a question that how can a poor farmer, a small farmer, afford them? So now we are developing mobile applications in which farmers can install smart applications and use those smart applications to get weed detection, to get disease detection, pest detection, to estimate the yield of the crop. And with these estimates, we can make a geomap of the whole environment. So now the time is up. So I would stop here. I would conclude my presentation here. And if there are any questions, the audience are welcome to ask. The moderators would be moderating the questions, I guess.
Thank you, Dr. Yasser Niaz. Now we are moving toward our last speaker, Dr. Umar Asghar from Nesh University, Islamabad. The title of his talk is Passive Brain Computer Interface and for Enhanced Human-Machine Interaction. Over to you, sir. There is some technical issue. Dr. Umar Asghar will join us shortly.
Meanwhile, if you have any meanwhile, if you have any question, please feel free to write in the chat box, and our speakers would be happy to assist you. Since we are moving towards the end of our workshop, we'll be having a panel discussion at the end of this workshop after Dr. Umar Asgar's talk. So stay with us, and meanwhile, please do visit our Facebook page. And for any other updates, please feel free to contact us through our social media platform. I guess Dr. Umar Asgar is here with us. So Dr. Umar Asgar is our last speaker of the day. The topic of his talk is passive brain-computer interface and for enhanced human-machine interaction. Over to you, Dr. Umar Asgar.
Hello and Assalamu alaikum all. Am I audible?
Yes, sir.
Okay. Sorry for there was some technical difficulty at my end, and I am trying to reconnect. Just a few seconds, I'm going to upload my presentation. Thanks. My screen is visible to all?
Yes, sir.
Okay. Bismillahirrahmanirrahim. My name is Dr. Umar Asgar. I am from Department of Robotics and AI from National Universities of Sciences and Technology, NUST, Islamabad, Pakistan. The topic on which I will be discussing and about we will have an brainstorming is about passive brain-computer interface for enhanced human-machine interaction. Basically, we at NUST in departments of robotics and AI, and especially in NCAI, we are working on the brain signals. The mechanical movements are the action, which while the thoughts are our electrical impulses, if we talk about mainly the EEG signals, and thought are faster than actions. So direct interaction with the world is, if it is done through thoughts, then it would be more in speed, and it will be enhanced. For generation, the idea of having intelligent machines that can read people's mind and react without direct communication had captured human imagination. With the recent advances in neuroimaging technologies like EEG, MRI, FNERS, the brain-computer interface has emerged as a new tool for making this interaction between the machines and the human. The brain-computer interface or the brain-machine interface, they are nearly the same terms that are used at different places, but they are more like the same. is basically the direct communication pathway between a brain and external devices. Research on BCI basically began in 1970s at the University of California, Los Angeles, under the grant of National Science Foundation and DARPA. Then the research goes on, and a lot of papers had been published. Basically from 1970s onward, a lot of work has been done. The field of BCI took momentum after, especially in the 90s and in early 2000, mostly towards neuroprosthetics application that we are also doing at NUST lab. And that aim at restoring the damaged hearing, sight, and the movement, the signals from these prosthetics can be used as adaptation and be handled to control different devices and different machines in a very ecological manner. Before going towards our actual project that we are going at NUST, I would like to have some basic concepts so that our wide audience could have better understanding about the BCI. The reason BCI works is because the way our brain functions. Our brains are filled with neurons, and the individual neuron cells are connected to one another by dendrites and axons. Every time we think, move, feel, or remember something, our neurons are at work. They move. There is some activity between these neurons. That work is carried out by small electrical signals that zip from neuron to neuron as fast as 250 miles per hour, right? These signals are generated by differences in electrical potential carried by ions on membranes of each neuron. Although the paths of the signal are, as you can see in the view file, by different electrical signals, and the scientists basically detects these electrical impulses and signals to use them, further translating into commands, and these commands are further given to the machines and computers to carry out different tasks, right? The basic principle of BCI are to decode the brain activity into a meaningful commands for machines, thereby bridging the human brain and the outside world. This is very important, that it basically is a sort of bridge between the human brain and the outside world. In healthy subjects, the primary motor area sends the movement commands to the muscles via spinal cord. But in paralyzed people or people having some injury in their brain or spinal cord, then that pathway is interrupted. So the BCI technology is very effective for these patients and paralyzed people. A computer-based decoder is used which translate this activity into command for muscle control, especially in case of the paralyzed people. We at NUST are basically working in BCI as well as neuroprosthetics. Neuroprosthetic is an area of neuroscience concerned with neural prosthetic signals using artificial devices to replace the function of impaired sensory organs. There are several forms of neuroprosthetics that are being used all over the world and also in our NUST lab to restore different functions of human body. We are working and research is still going on how to restore vision and also the hearing ability. And the BCI, on the other hand, is very similar to neuroprosthetic, but it connects the brain to or our central nervous system to the computer system. And the most commonly used BCI system in our lab are FNIRS, that is functional near infrared spectroscopy, EEG, fMRI, on the other hand, is non-invasive, but due to its heavy protocol, so far we are not using it. And invasive technology, ECOG, it has certain limitations as far as concern to the human health and its safety. Now coming over to the passive BCI, we have talked a lot about the BCI, but we should be somewhat clear about there are different terminologies that are being used in the BCI domain. One is the active BCI and the other is the passive BCI. The brain activity features extracted for the BCI classifier induced by the user active control or measured as a response to external stimulus. Such active BCI requires user to get involved in cognitive tasks and provide explicit commands. Means that in active BCI, a user intentionally carry out few tasks either on its own will, or it is being guided in an experimental setup to carry out different encoded tasks. These are the indirect tasks to generate few signals that are further used to move and translate into commands for the machines. However, in the case of the passive BCI, that drives their output from spontaneous brain activity without the need from the user to perform specific mental tasks or receive stimuli. This passive BCI is much used in neuroergonomics applications, where normally monitor longer epochs of the brain activity for detection of cognitive state change in case of passive BCI, and we will have a deep look into it in the next few. Then is the passive BCI and the neuroergonomics. Basically, extraction of such higher order information from brain signal is seen as a gateway for interaction between humans and intelligent systems like robotics. Passive BCI provide a promising channel for prediction of user cognitive and affective state for development of user adaptive interaction. Neuroergonomics, that is basically brain network, and that what we are basically majorly working at our NURSE lab in precisely, is the investigation of human brain in relation to the behavioral performance in neural environments and everyday setting. This is basically brain network. Ergonomics is a field, as we all know, that it relates with our ecological environment in relation to human being. And similarly, the neuroergonomics is the relationship between our brain and our ecological environment, and how we react to different processes, and how these processes are made as conducive and comfortable depending upon the human body and its brain. The different sort of emotions can be used in neuroergonomics that can be used as further in passive BCI, and the most used signal all over the world and also in our lab is the mental workload. Mental workload, monitoring of real mental workload and vigilance of a particular importance in especially safety critical environment. Passive BCI that detects drop in attention level and increased mental fatigue can be utilized in broad range of operation environment and application domains, including aviation and industrial workplaces, where the safety and efficacy are important, as well as educational and healthcare setups, where the system can provide feedback from learner to the teacher. What we are doing here at NURSE is basically we are measuring the mental workload from the operators that are either working in aviation environment, like the pilots. Also, we have recently won a Horizon 2020 project that is the Enhance, that is enhancing the human interaction with the socio-technical system, where we measure the mental workload of the operators that are working in vessels, the naval ships, and all those workers that are working in industry, and how we can optimize the environment that is interacting with these operators in these settings. So this our Horizon project is basically modeling of the KPIs and the training variables for these operators that are working in these harsh environment, and how to optimize these factors, these variables like mental workload, fatigue, their intention level. First, we have to measure them, and then we classify and then optimize the system that interact with these variables. This is a depiction for the closed loop human robot interaction using the passive BCI, where the data is acquired in form of either EEG or the FNERS. Then the signals are being processed in the computer system. Then these cognitive states are detected, and the signals are then passed to the robots for different actions. And these different actions that the robot perform as a result of the signal acquired from the human brain, it performs different activities, and the human being get feedback from these activities that the action which he or she perceived to be done, or whether the robot is doing or not. So it is a sort of closed loop system. The first FNERS device that we developed in our lab at NUST is, as shown in the view file, it is basically a very lightweight portable device. The FNERS is a passive evaluation of user responses during robot interaction, for instance, detection of cognitive workload during multitasking with two robots. And basically, its design principle is based on a theory that the blood hemoglobin carries oxygenated and deoxygenated blood. The hemoglobin is either oxygenated or deoxygenated. And based on our activity in the neuron, the similar analogy can be drawn from the activity in our muscles as well, that if we move our limbs or legs or any part of our body, the blood circulates. And if we move our muscles, there is a requirement of the oxygenated blood, and the deoxygenated blood goes towards the lungs through heart, and then it becomes oxygenated and again come back towards the activity area. And similarly, in the brain, whenever neurons are in action, means some activity is being performed or encoded, then the neuron requires this oxygenated blood, and there's a change between oxygenated and deoxygenated hemoglobin in that activity area. And this change is basically detected by this function near infrared spectroscopy system, that is the FNERS system that we have recently designed in our lab, and it is working well, and we have so far performed various experiments. In this slide, we can see that the complete setup is shown, that how first of all the brain signals are acquired, then they are sent acquired from FNERS system, then they are sent wirelessly to the computer system. There in the computer system, different pre-processing is done. Then the feature engineering after, then the machine learning or deep learning is performed. The signals are segregated and the commands are generated to the system. This is the basic architect of our FNERS device. Here, as I previously elaborated, that the FNERS system is placed on our prefrontal cortex area. Two wavelengths are used in our device. 760 nanometer is used to capture the changes in concentration of oxygenated hemoglobin. There is 850 nanometer is used to capture the changes in concentration of deoxygenated hemoglobin. These light intensities are converted into concentration changes of oxygenated and deoxygenated hemoglobin. in the processing stage in the computer system. And then when near infrared light propagates in the brain tissue, forming, you see a banana-shaped curves due to the scattering from the molecules as it travels from sources to the detectors as shown in the figure. So basically this whole technology relies on the optical properties of cerebral blood flow to infer the brain activities. Now coming over to the mental workload and the passive BCI that we are working, and we have already come up with various results that I will show you in the coming slides. This was the arrangement that we did in our experiments that we did a few months back. Here the data acquisition is done with the help of FNER system from the prefrontal cortex. The signals are required, as I mentioned earlier, that oxygenated, deoxygenated hemoglobin signals are basically used to further generate the signals for pre-processing, then the feature extracted, data processing, and then mental workload signals are segregated based on their different difficulty levels. So basically mental workload is segregated on its difficulty level, and we have used different machine learning and deep learning techniques to segregate these signals. We have recently decoded 4-class mental workload, which was very new in this area, because so far only 3-class mental workload were decoded and classified, and we decoded and classified 4 class of mental workloads as shown in the figure. The brain activity signals are required from prefrontal cortex of the brain. We performed supervised mental workload experimentation on different subjects. Real-time 4 mental workload states were assessed using FNER system, and initial classification was performed with different machine learning techniques like SVM, KNN, ENN, and LDA. And in parallel, we also performed deep learning techniques like CNN and LSTM, and they performed very well in case of the mental workload classification. This is again the validation of our results in the experiments that we performed in our lab. The NASA, the National Aeronautics and Space Administration Task Load Index is the measure that basically it is a subjective multi-dimensional assessment tool initially designed for pilots and astronauts, and now it is considered as a gold standard that rates mental workload to assess the task, gauge its cognitive load demands, effectiveness, and performance. Our experimental paradigm is basically validated with this NASA TLX and its 6 subscales like mental, physical demand, temporal demand, effort, performance, frustration level of the subject are basically classified and validated with the NASA TLX. And as we see that the TLX score of mental workload 3 is greater than mental workload 2 and is greater than mental workload level 1. These are the results that we obtained with the of mental workload classification with our classifiers of machine learning results that we obtained. Here we can see that the 4 different mental workload states are easily segregated using SVM, KN, and LDA classifiers, and then these signals are further translated into the commands. These are the results of our deep neural networks. Here, the deep neural networks outperformed basically the machine learning classifiers, and their accuracy was more than 85%. It varies between 85 to 95% in case of deep neural networks. And as I mentioned earlier, that we choose CNN and LSTM, and LSTM was actually more better in terms of classification. We also applied these mental workload signals because previously mental workload signals were only used as passive BCI, neuroergonomic signals, to monitor a few activities that a person is facing, or designing the environment of the person based on these neuroergonomic changes in the brain. But we tried to use these mental workload signals to operate the actual prosthetics, the actual machine, with the help of passive BCI. The integration of neuroergonomic, the brain-machine interface systems are considered here in our case. We basically, here in that case, since we used two commands to open and the close of our prosthetics. So two-state mental workload were classified here. And the bionic hand is completely wearable in that case, capable of controlling 5 fingers independently and separately. Data was acquired from PFC and feature engineered and then classified and generated into the commands to operate this bionic arm. Here it is again a clear depiction that how we did the mental, how we acquired this mental workload 1 and 2 with our FNER system, and then the pre-processing, feature engineering, classification, and then these 2 classes are fed into the bionic hand to operate it. This is the depiction of hemodynamic response of controlling commands for brain-machine interface. Both machine learning and deep learning classifiers were used to generate these commands. Here we can see that the HRF, that is the hemodynamic response, is basically used to operate this bionic arm in the form of open and close. This is the demonstration for different neuroergonomics application with the mental workload. This figure shows that the accuracy with the deep neural networks as compared to the conventional machine learning algorithm are much better. And the average accuracy that we obtained with the LSTM was 89.3%, which is quite good, and the accuracy is much better as compared to the previous researches that were being performed. And as we can see that these mental workload were used in our research for the first time to operate the actual prosthetics and the bionic arms, and which is kind of novel in this BCI domain. At the end, I would say that the passive BCI technology hold promise in extracting effective and cognitive state for an optimized human technology interaction in real-world application. Their possible employment in human-robot interaction with intention to inform the HRI community of the promises and the challenges of passive BCI technology. The future work should continue to advance the synergy between the two domains and further explore the impact and effectiveness of BCI-driven robots during closed-loop interaction with humans. With this, I thank you all, and thanks for listening. And I welcome your question if you have any at the end during the panel discussion. Thanks.
Thank you so much. Thank you so much, Dr. Umar. So to conclude this fruitful workshop, let's have a short panel discussion with our 6 speakers. We have Professor Dr. Yasser Ayaz with us, Professor Dikai Liu, Dr. Wajahat Mahmood Qazi, Dr. Yasser Niaz, Dr. Umar Asghar, and Professor Kosugi. Due to some urgent issue, Professor Kosugi had to leave, but it was great having him with us today. This panel discussion will be hosted by Dr. Sara Ali from NUST. Dr. Sara is an expert in human-robot interaction. Topic of our today's session will be intelligent robotic for practicality, what the future holds. Over to you, Dr. Sara.
Thank you. Hello, everyone. Thank you to all the speakers for your insightful speeches. We will start with the panel discussion now. Please let us know if you have any comments from the guest speakers, please. Then we will start with the few questions from the audience. Okay, so the first question for Dr. Yasser is for the related to the prosthetic foot, that what does it take for an industry to commercialize and mass produce such product? Sir.
Right. So the question is like very much dependent upon the area in which we are trying to commercialize a certain product. Like, of course, first any industry has to see that if the the basic items required to put together that kind of foot are available in their vicinity. Of course, a lot of things have been made easier by like, for example, many developing nations that are coming up, like China, for example, who are doing manufacturing in a very like cheap, cost effective and with a good standard as well. So I think that commercializing such products in the present world is much easier compared to like what it used to be in the past. But first of all, like I think that in the industry as well, there has to be a receptive, like especially looking at the Pakistani scenario, there has to be some positive receptive element towards adoption of technology for solving problems. So if they are completely satisfied with whatever solutions they're offering before and they don't want to advance to new ones, so it will take some effort to convince them as well. So I think the first thing that is required is a will to use advanced technology to actually solve their problems. And the job of researchers is to demonstrate that practical solutions exist. To file patents, to prove their novelty, to prove their effectiveness, and of course to try to bring the technology into a form where it is affordable and possible to be commercialized. And then of course next for the industry, the will is most important. And the second thing is that as I've seen with most of the industry today, that the startups, for example, are there like you could say shopping marts actually. So whenever I've seen like in Barcelona and Mobile World Congress, in GITEX, in many other exhibitions that take place, established companies are going around startups. So I guess that if you want your product to be taken up by a company and actually market it somewhere or actually turn it into a product, it's better to turn it into a startup first and demonstrate it in the form of a startup. In that way, somebody can take it up from there and then commercialize. That's my view on it.
Thank you. Thank you, sir, for your comments. Sir, the next question is for Dr. Dekai. The audience is asking, what are the biggest hurdles when you try to replicate the animal-like natural movement and motion in robots using actuators and motors?
Sorry, thank you very much. As I mentioned when I was showing the video of how ants move from one place to other place and transfer from one object to other object, and we learned a lot from there. But unfortunately, at the moment, the engineering technologies available in the world is still very limited. So we are not able to develop a leg or actuator which has this kind of high torque to weight ratio, which allows us to design a robot which is capable as an ant. So that was the reason we moved to look at the inchworm rather than ants. So definitely the biological system and including people, animals are so well evolved. So it's very difficult for us, for many scenarios, it's very difficult for us to develop a robot which can really mimic the real biosystem. Thank you.
Thank you, sir. Thank you for your comments. The next question is for Dr. Wajahat. The audience is asking, in Pakistan, how much significance is being given to cognitive robotics, and what is the extent of development in it, particularly in Pakistan? Thank you.
Well, when we talk about Pakistan, it's pretty much new idea in Pakistan, because in Pakistan normally am I audible now? Okay, so in Pakistan, when we talk about cognitive robots, it's pretty much a new idea. So regarding significance, I think in universities and even in our industries, the primary goal should be this thing, that we should encourage our students and every stakeholders to bring in robotics in the industries, and to teach students regarding general robotics. Cognitive robots is pretty much new in Pakistan, so I think that it will take 3, 4 more, 5 years where we'll be looking around the cognitive robots here and there. Yeah.
Thank you, sir. So the next question is for Dr. Yasir Niaz. How far is local technology from having the drones for surveillance being implemented in Pakistan?
As far as local technology is concerned, I know some groups who have designed their quadcopters or octocopters. So they do take parts from the market and do assembly. Yeah, but as with most of the industrial processes, there is not much progress in that. Pakistan is very good in IT sector. So I guess as long as we take off-the-shelf solutions and produce very good software solutions, we can do leaps in technology, in advancement. But engineering sector should also catch up, and they are catching up. 3D printing is also one shortcut through which we can reach those limits. But that also involves policy matters, as Dr. Yasir Ayaz knows very clearly that 3D printers are still, I think, banned here. So if we allow such kind of technology in Pakistan, then we can advance really nicely locally as well.
Thank you, sir. Dr. Dekai, we have another question for you. How federated learning models deploy in robotics application? Like if we talk about wearable gauges to measure the heart stroke and neurological attacks, what about that? Thank you, sir. Sir, I think so. The mic is mute.
Sorry. So again, I'm not doing that very much research on machine learning, although I'm doing some related. But my understanding of learning really is there are huge challenges really associated to learning in robotics. For example, you can just use the learning algorithm for image recognition or for other applications. But in robotics research, it is quite challenging, mainly because we don't have much data and we don't have much, for example, scenarios which we can repeat. And the robot operating in real environment is very difficult to collect data. And even you have some data, then this data may not be enough for you to train a learning modules that can be really used to help to improve the performance of the robot. Thank you.
Thank you, sir. Dr. Omar Asghar, we have a question for you. The latency of signal from brain to mechanical movement, what factors apply and how that latency can be minimized?
Am I audible?
Yes, sir, you are audible.
Okay. In fact, this latency or the delay in terms of the brain signal to these mechanical devices are basically catered with different techniques. Like first of all, if we have devices that have better temporal resolution, like the EEG, then the one way is to reduce these delays. The second is our experimentation settings and our experimental paradigm, that how we can cater this latency or these delays. For example, if we reduce the task duration in terms of second, then there is some optimal bracket, maybe from 7 to 9 seconds, that the delays are minimized. And before 7 seconds, if we have the task that is of too less duration or too greater duration, means more than 10 seconds, then the delays will be more. Similarly, in terms of classes, if we have more classes to be classified for generating the commands to the machines, like we had the 4-class mental workload, then the delays will be more as compared to the 2-class classification, and further translation these signals to the bionic arms or to the robots. So there are different ways. As I discussed, first of all, is using different devices that have better temporal resolution, and secondly, we can cater this within our experimentation settings if we are using a single device and having different sort of experiments on the participants. Thanks.
Thank you, sir. These were the all questions from the audience. Now I would hand it over to the organizers of the please. Thank you.
Thank you very much, Dr. Sara. Professor Dr. Yasir Ayaz, would you like to have another follow-up question or answer, perhaps a discussion, since we have some time on our hands, sir?
Yes, sure. So I think like we can open it for the audience if anybody from the audience wants to ask a question. It would be good to have things interactive.
We have a few more questions that I just saw.
Right. So like you see, like
okay, sir.
The challenges of robotics are different from, if you allow me to ask a question, can I ask a question?
Sure, sir, sure.
Okay, so like, in our experience of working in different places with robotics, like I've lived in Japan and studied there and worked there as well. And then we worked jointly in collaboration with other countries too. So maybe all the speakers one by one could shed some light on, how like the robotics, the development of robotics industry, in what ways it is different, in what way it is like similar, and how do they see it evolving in terms of increased international collaboration in the years to come? May I ask Professor Dikai, you to actually enlighten us, because of your experience with organizing so many of these workshops with so many countries. I think you're the best person. So your mic is mute.
Thank you very much, Professor. Yes, definitely international collaboration is very, very important, particularly for researchers. My experience here is really we have been trying very hard to work together with people in around the world, and we have the joint centers with, for example, the Washington State University in the U.S. and the university in China and in UK as well. And we provide travel funding for people to come to our center, and also to support our people to to other universities to conduct collaborative research. So this definitely is very important. I understand probably, I'm not sure for Pakistan, maybe probably you must have a lot of this kind of activities as well. I think particularly for younger researchers in robotics, this kind of collaboration is so important. So encourage them to communicate with people, to try to work together with other researchers in other countries are very important for their future. So definitely.
Definitely. Thank you for enlightening us. I think Dr. Yasir Niaz also conducts a regular workshop with German partners funded by DART. So Doctor, what's your view in terms of what you see in Germany and what you see in Pakistan? Like what's similar, what's different, and how do you see the collaboration progressing?
We are very happy with our German collaborators that they have been collaborating a lot with us, and they are very open to us. They discuss the problems that are faced in the world, And the German government is also very keen to look towards developing countries and solve their problems. That is true. The difference that I see is amount of funding available there and here. There's a huge gap in that. The amount of infrastructure available, the amount of public funding as well. Recently, the Pakistan higher education has also increased the funding and established the national centers of excellence all over the country, which is a good initiative. So I think that things are moving in the positive direction, but still there is a lot of gap in this funding available, the opportunities available for researchers and especially young researchers to capture those opportunities and perform as good as they can.
Right. Thank you, Dr. And I think I think it's more or less similar for everybody. Does any other speaker want to comment on the same question? All right. So, Dr. Wajahat, you've been working on cognitive robotics for quite some time in Pakistan, and I think that such kind of application, such kind of products can have great application, particularly with banks and a lot of places which require direct interface with humans and human-like objects, which could be robots or animated characters. So, have you taken on the industry for this kind of product so far? And because of course you're running a company too now, and what's the take on this? How does the industry receive this kind of products? Do you see a light at the end of the tunnel?
Yeah, I have both versions, like a very good experience also, and a pretty so-so experience also. I won't say it bad, but it was so-so. Well, in few sectors like e-commerce and other stuff, I have observed that they are pretty much open-minded, and they're accepting these kind of technologies, and they are really willing to put these technologies into play. Well, my personal experience regarding few of the factories and industries over here in Pakistan, they were really one of the engineers said to me, really, can we do such kind of automation? So there was some these kind of arguments also. So I think that once we pitch them in the right way and we are reasonable in telling them that what kind of applications and how they can actually improve their ROI, they're pretty much open for it. So I think that with right team and with our IT and other robotics partners, they are pitching these technologies in right way with good arguments, and particularly focusing on this thing that how they can generate more business and stabilize their ROI. They are open for it.
So that's encouraging to hear, I guess, in a lot of ways. And by the way, another researcher with us here who has extensively worked on practical robotic applications and interacted with a lot of subjects, human subjects, is Dr. Sara, who has been anchoring this session. So, Dr. Sara, may I ask you a question?
Excuse me, Dr. Yasser, I think Dr. Sara has some internet connectivity problems, so she's not here currently.
All right. Well, she has done remarkable work on related to autism and using robots practically with children. So I wish that we could showcase it. But anyway, it's okay. So Dr. Umar, if you allow me to ask you a question. So you have won the first Horizon 2020 project of Pakistan, the collaboration with Norway, Germany, UK, and a lot of international countries. So can you, for the benefit of the researchers that are participating here, I think a lot of people from various countries may be partnering up with Horizon 2020 partners and European Commission and partners to actually try to win funding from there. So what were the challenges that you faced, and are there any tips on how to build a good, successful international partnership?
Thanks, Dr. Yasser. Am I audible?
Yes, you are.
Okay, thank you. In fact, about the Horizon project, yes, indeed, it is not new in the world, but as far as Pakistan is concerned, there are very few. And NUST, our university was the first one to got that project. And first of all, I will like to talk about the challenges. The challenges are, first of all, to search for good collaborators and the international partners that have inclined to work with Pakistani universities. So that was the biggest challenge. But that challenge again can be addressed if we have solid research and if we have some practical applications that these foreign universities and their key researchers see in our universities and labs, like we have a RISE lab at SMM in NERST that is being headed by Dr. Yasser and his team. So if these sort of labs and active output, research output is being portrayed, and if it is visible to the world, then yes, we can have good collaborators. And secondly, as far as it is not a challenge, but it is again a sort of, you may say that objective, that what's the biggest challenges that are being faced to the globe as a whole, not as a Pakistan, because Horizon basically targets the challenges that are being faced to the humanity all over the world, and not to a certain sector of the people that are living in some country or in some region. So we should have a solid objective idea, the problem statement that the humanity is being facing today. So that is basically appealing to these Horizon reviewers and those sitting in the European Commission. Thank you, Dr. Yasser.
Thank you, Dr. Umar. I have another question for Professor Dikai Liu, if it's possible. Sir, I would like to ask you regarding, we see like people like Elon Musk and, the new age of trying to explore development on Mars and building, habitats under the sea and all sorts of new kinds of technologies where people are trying to build structures in other places in the world. So first of all, what is your take on the practicality of these ideas? And second, do you think a lot of applications of robotics will increase in the world because of these newfound applications and new places where they want to construct things?
Yeah, in general, I think that is the case. And we saw the videos and from DARPA, and you see the Mars rovers, and particularly in the Mars, and they start to operate, and which means the robot or the drones are good enough really to operate there, right? So in the future, definitely, from my personal point of view, I do think we're going to see more and more robots with intelligence that will be deployed in practical applications, either on the Earth or in the space or other places. So definitely, but again, still, we as a researcher, particularly for younger researchers, and probably when you do the research, probably think about how much practical constraints you will be able to address in your research. And that will help you to think about how far your research is away from the practical applications.
And that's a very good aim to be targeting, yeah, to really realize how far we are and to try to develop applications in a practical direction. Dr. Yasser Niaz has done some work with a very prominent Pakistani industry, agrochemicals, and he was working on drones for targeting. I think your talk today was also related to that. So, Dr. Saab, what is your take on Pakistan's industry side? Like relating with the first question that I was also asked, like, how is the Pakistani industry's take on like commercialization and adoption of robotics in their normal methods?
As far as I have seen the industry, they are more getting towards AI, data science, and machine learning, not towards robotics. As of now, there are very less number of industries which are doing their ventures in robotics. But now it's a positive sign that a lot of industry is coming towards AI, machine learning, and data science. They are making their own full divisions for AI teams, AI divisions, AI offices, even AI sub companies as well. So once this AI business picks up and we have machine learning and AI solutions for the industry, I hope that they will also start developing these solutions for robotics as well, and introducing robotics applications as well. So far, I think all of the robotics that is being deployed in this industry is simply imported as end solutions deployed there, and then we try to develop local maintenance solutions for them.
Right. And Dr. Omar, there's a question for you. That are the brain signals being analyzed taken from our spontaneous thoughts, like in general, not just in your research, but in general, are they being taken from our spontaneous thoughts of the subject, or are they taken from the signals which used to move our body, which don't require any thought? So which one is it? And how far have we gone in terms of manual dexterity? Like, for example, writing, playing piano, painting, like what sort of brain signals can we extract until now, and how much of these can we literally translate into robotic motion?
Okay. Thanks, Dr. Yasir. First of all, regarding the first part of question, that whether these are spontaneous thoughts or the actual body movements signal. In fact, the studies exist for both the cases, the spontaneous thoughts as well as the motor signals. And the results that we obtained from motor imaginary signals are much superior as compared to the spontaneous thoughts, because in order to move a device or to send some command, the signal has to be strong. So for that, we need to devise some encoded signals that are basically the indirect signals, which are not the spontaneous thought. They are motor imaginary signals. They are quite strong. And these strong signals are basically detected for then translating into the commands and then into the BCI systems. And second, the part of the question was regarding the writing or other BCI applications. Yes, the BCI has so far achieved the active BCI. Certain human beings which are paralyzed or in the state of disease where they cannot move their fingers or hands, then yes, they can write up to a certain level, but the accuracy is so far not 100%. The accuracy is in 70 to 80%, and still there is a lot of research is going on in writing, that how to translate the brain signals to write actual words. And there's a lot of research that is going on, and other things as piano, playing piano or painting. Yes, playing piano and painting are also the active area of research in the BCI. And again, the accuracy is not more than 90% in all these cases, but still research is going on, and the researchers are devising new ways how to filter out these inaccuracies and how to increase the performance as well as the optimal accuracies in writing, playing piano or painting, etc.
Thank you, Dr. Omar. That's insightful. And I think like this question was targeting artists, like the bioprosthetics for artists. So we get the answer that things are progressing in that direction, and yet we may be a little far from like a very accurate control of devices for the artistry work, but we are getting there. So research is going in that direction. Thank you for the question, Dr. Sohail Chughtai. Then we have another question. I think this one can be addressed by Dr. Wajahat, that how can we reduce the computational cost in like various robotics and AI applications? Like the questioner, Dr. Uzair Iqbal, has asked regarding healthcare robotics, but I think this applies to nearly the entire area of robotics, because right now utilizing a lot of data, drawing conclusions from like machine learning based methods and like applying them in real life applications is a concern that is it's widespread in all of the robotics area, not just healthcare. So how can we reduce the computational cost in the robotics, artificial intelligence applications, especially if you're working on CNN models?
Well, I'll take it as a, I'll reply to this question in a very general way, because it's a very common problem when we talk about AI and machine learning, or matter of fact, artificial neural networks or deep learning things. So not only in robotics or particularly in healthcare, we are facing this problem really in every domain and in every direction. So I think that this problem is very common. So first thing is to follow the best practices. Whether if you're targeting the health care domain, or you are working in the area of textile industry. So whatever the domain you are working, to try to look into the literature that to see that what are the best practices recommended by the practitioners. Secondly, what I have observed personally is that what we normally do is that we simply go for pre-trained models, and sometimes we look for the solution from GitHub and all those sorts of things, without looking into it, that how those models were actually configured based on their hyperparameters and all those things. So I think that one must have a very better and deep understanding that how those hyperparameters are actually tweaking the internal configuration of your CNN or any architecture. So once having those understanding, we can play with those parameters based on our experiences. And obviously, there is no thumb of rule that you do A and do B and then you get the best optimal performance. So you have to rely on your past experiences and you have to go through the empirical fashion. This is what I think that it could be done. Yeah. So the best thing is to look into the hyperparameters, that how you can speed up the entire learning process.
Okay, that's a very good answer. And there's one more question coming into my mind, which any of the speakers can try to address. Like, some of the movies have showcased robotic sports. Like, for example, there was a movie which showed robotic boxers taking on each other. So do we perceive that as a reality, like robotics coming into the entertainment industry? Of course, there are things like robot wars already, but like they're not mainstream like that, which is shown in a lot of the movies. So do we see robotic sports evolving like as a mainstream sports in the future? Would anybody like to address that? Maybe Dr. Yasir.
I may allow.
Yes, Dr. Jahad, please.
Well, yes, I think that it is going to be the future, because by integrating robots with augmented reality, you see, you can actually bring those gaming into into your practical physical space. I think they think that is very something different avenue which we can actually explore. I have observed few prototype games in which they have actually placed drones, using drones with augmented reality combined together in a sport fashion. I think that it is going to be something which we'll be looking for in the future, not far future, in the future. Yeah.
And do you think that, like, for example, we have Nintendo and we have the Wii and other like computer games kind of things right now? Maybe we'll have a robotic game kind of engine coming up and soon, which will like give us real exercise as well.
Yes, that is the future. I think that it has to be done one way or the other way.
Right. So I think that one thing, because like if there are any other questions from the audience, they can also comment. And one thing I would really like to learn is that for each one of us, what are the next big avenues of research? Because the talks were also interesting. So what are the next big avenues of research that we are targeting for our respective areas of work in which we have presented here? So may I start with Professor Dikai?
Okay. I would think in the future, human-robot working together, or human-robot teaming. I think this could be a good and has a very good potential in the long-term future. Because not only from the social aspect, but also from the helping people, like aged people, disabled people, and even the normal people in the work environment or at home. So this is what I think it has a bigger future.
Thank you. And Professor, do you think that like robotics coming into the industry or coming into the everyday life will reduce some jobs for humans, or how the job scenario will evolve? Because this is another fear that people keep expressing.
That's right, yes. And many people are talking about this and are asking these questions. And automation is going to reduce the number of jobs currently available. But on the other hand, and automation is going to increase more jobs. So this is why if we look at back at the computers, right? Once we have a computer system and plus software, many jobs have gone. But again, the computer system just increases so many different types of jobs. So this is one thing. Second thing is that from a robotics researcher point of view, we are doing robotics research. We're trying to advance the technologies. But at the same time, as a researcher, I guess it is part of our responsibility to help people as well. So while we're creating technology to automate some tasks at the same time, we should just focus on, say, to create opportunities for people as well.
Right. Thank you. That's a very insightful and very positive answer for a lot of listeners to hear, and that's the bright future that we are all looking at. Dr. Yasir Niaz, what's the next big thing that you are targeting in your research?
On the industrial front, we have come in contact with a company which is getting a project on robotics, autonomous robotic drones, which are supposed to cover an area of 4 to 5 kilometers. So we are in the initial talks with them to make some collaboration with them. So that is a good thing that a Pakistani company wants to develop a local drone solution. And in the academic research front, I have come in contact with some researchers in UK who are who also again wants to do some projects in agriculture, in large scale agriculture, using embedded systems, using long range sensors to monitor agricultural fields, and somewhat going towards water management as well.
Okay, very interesting indeed. Dr. Wajahat, what's the next big thing in research that you're looking at?
Okay, when talking about the industrial front, I think that particularly with reference to Pakistan, that is to optimize the people's expectation. I think because sometimes the people are over expecting and thinking about so many advanced things that could happen in industry, and or they're having very low expectations. So I think that as being moving into towards the industry side, I think that this is something which we need to do something to make these people realize that this is the actual place and the technology where robotics can help you in a very optimum way. So let's not put our hopes very low or very high. And with reference to academics, that would be a very crazy idea because for last couple of months, working in academia and industry, and due to all these COVID things, so I was like wondering that how can we make these machines realize that how much effort we are putting to make them intelligent and self-aware. So whatever the effort we are putting, these machines does not have any idea what we are really doing for them. So how to make them realize this thing? And I don't have an answer to this question. Maybe.
Yeah, a lot of research is evolving in this. Yesterday, I was reading that people are introducing food lockers, a new concept of, for example, instead of when you come to take away food from a certain place, instead of coming and like taking it from the hand of a human, it might be placed in a locker and you extract it from there. So maybe the time when robots may be delivering food is not that far away, but how accurately drones can do that, maybe Dr. Yasir Niaz can have some idea about that. And recently, there was some news about Kareem using drones to deliver items in Pakistan. Is that true, Dr. Do you know any details about that? Dr. Yasir?
I haven't come across any demo or video of that, but I have heard about Amazon delivering stuff, and also this AliExpress and Alibaba, these huge players, they're also talking about that and doing demos. So I guess they would probably be the second company after Amazon to deploy those drones, delivery drones.
Right. There are some pictures of that
in
with Kareem as well. Yeah.
Yes,
yes,
in Lahore, Airlift was providing such services, but that was that old traditional mode, not autonomous.
So it's good news that robotics is gradually becoming mainstream, and drones no less than any other technology. Dr. Umar, what's the new big thing? What's the new exciting thing that you would like to target for your next big thing in research?
Thanks, Dr. Yasir. In fact, the BCI domain goes hand in hand with the robotics and the AI. For example, if a main robotic guy builds some autonomous vehicle, then this autonomous vehicle gets some feedback with a BCI device from the human being. For example, some human is sitting in the autonomous vehicle, and some correction is is being provided to that vehicle through a BCI system. So in terms of the AI and the robotics, the BCI will be in parallel. And another example would be like, as you mentioned about the drones. Now the MIT guys are working on the drones which are being controlled by neural signals, and the commands given to these robotic drones are through our brains instead of some manual commands through a joystick, or even if they are autonomous, even then some correction may be needed, or some path planning, things like that. So it will go hand in hand. And another participant in this discussion mentioned about the handwriting recognition and the playing piano and the other stuff like that. So it is the future of BCI. So it's a promising, and it would, inshallah. Thanks,
It's a
Dr.
very interesting answer, and like I think that like it's also insightful in another way. And also we know that you're an expert in socio-technical systems as well, and you worked on systems in which humans and machines like work together, or humans are in loop. Like for example, for the benefit of the audience who may not know, so systems in which, for example, a pilot is flying a plane where there is a significantly complex technical system, and the human, is trying to operate that system. So Raksha, do you think that there could be some, like based on your study of socio-technical systems and mental workload in operating the complex socio-technical systems, what are the main key, you could say, areas of livelihood or daily work in everyday life that you feel are good candidates for like being replaced by robots? Like for example, where autonomy could be developed, and those systems may not be good for humans to work on because they're very heavy in terms of mental workload or something. So in which systems do you think autonomy definitely needs to come in quickly because the mental workload is overwhelming and maybe humans can't handle it? Are there any systems like that, or maybe we are reaching too far?
Thanks, Dr. Yasir. In my perspective, autonomy may lead maybe most of the areas that we see today and in the coming future. Only the robotics may lag behind in terms of emotion recognition domain for certain period of time, even though some research is going on how to detect human emotions and translate these emotions to read by the robots. But I think that is some technology of the far future. Otherwise, in all other domains, the robotics and the autonomous systems, intelligent systems, it is the future, and the things are being built on these systems. And secondly, you mentioned about the socio-technical systems that we are working in our projects. So these systems basically requires the performance optimization of the human operator using AI and robotics. So these are basically coupled to each other. At the one side, the human being is giving correction commands to the robot, and at some period of time to the AI algorithms as well. And on the other hand, in the socio-technical systems, the system is providing an intelligent feedback to the humans that how to optimize their systems and the processes. Thanks, Dr. Yasir.
Thank you. It's a very good answer. And I think like a lot of the audience listening to it will get many new ideas from this whole discussion, and particularly from your answer. Professor Dikailu, if I may ask another question. There is like, you know that in UNESCO, they were working on a standard setting instrument, a document for setting standards on robotics. And now they're working on artificial intelligence, the ethics of AI and ethics of robotics. And like when they come into mainstream, and for example, if an accident happens, how you actually lay responsibility. Like when a robot is working in the industry, for example, and if an accident takes place, so would the responsibility lie like with the manufacturer of the robot, with the operator of the robot, if there is somebody who programmed it, with a human? It's a very complex phenomena. So with humans and machines working together, what's your take on this? How do you see legality and ethics evolving around that?
Yes, this is a very good question. Thank you. And I've been discussing with many people, lawyers, and researchers doing ethics research or human factors. They don't have answer at the moment. Whose responsibility? There's no answer. I guess this is a kind of open-ended question at the moment, and I've been really trying to get the lawyers and the robotics researchers and the engineers try to work together to do some research related to robot plus law or robot plus ethics or robot plus AI. I think there are a lot of research that have to be done before come up with a kind of regulation or law. Probably this could be different from countries to countries as well. For example, people are saying, if we are going to have so many robots, then people will not have a job. How are we going to survive? Then people say, okay, that is okay. Then you can just say, ask the robot to pay tax. So if you use one robot, then you just get the robot to pay tax. So for example, and then get people to do something they are more interested in. So this is an open question, and I do think collaboration or research together with lawyers and with other researchers, that should happen, and it will happen.
That's good to hear, and I think that we have to go a long way yet, before we get to answers of these very big questions. Yeah, and especially with deliveries and all these things, starting with robots and robots already working in the industry. But so far, I think that as the autonomy increases, probably things may change, because robots have been working in industry for quite a bit of time. But it's easy if they're not making a decision to call it a mechanical fault. But if they're making a decision, then it becomes more complex. What do you think?
Yeah, that is the case. That is the case. And people make mistakes, right? And we make mistakes, and in every day, doing the tasks, and the people working in industry, they make mistakes. And in the future, robot is going to make mistakes as well. Particularly with more and more intelligence, and particularly implementation of AI in robotic systems, definitely there are going to be many mistakes to be made by the robots. So that is why it is important. Yes.
Another thing that I was thinking that may be of interest for you as well is that because robots are manufactured in different countries, like some are manufactured in Japan, some in China, some in the US, and the training data sets also vary from one place to another, right? So maybe if the same robot is taken to work in Saudi Arabia or deployed in some place in Africa, maybe the condition will be very different, and maybe even the availability of data for the robot to be trained on, for it to be deployed in that place, may not be that simple to actually solve. So what sort of mechanism do you think we need to make in a global robotics context that, for example, if we want to develop robots to deploy in developing countries, what sort of ideal partnership should be developed between developed and developing countries so that solutions developed can be globally acceptable?
This is a very good question. Just like the cars, for example, in Australia or in UK, and the way to drive the car, which is on the different side of from many other countries. So, this is a very simple example, and particularly if this is related to culture, right? If this is related to culture, then it becomes more challenging and more complicated. So, having a robot which can be used in everywhere in the world, I guess that may not be a good idea. So a robot, if this robot is going to be used for a particular region or country, this robot has to be adapted to that kind of environment, to understand the culture, understand how people work, and understand how to help people. So probably in different way. I guess the robot has to be trained, or the robot should have some intelligence which can be adapted and can adapt to different applications.
That's a very interesting concept and a very interesting answer actually. So the machine learning has to somehow step in to actually help cope with that kind of difference. Very true. Dr. Wajahat, may I indulge you in a question? So, like for example, what kind of new jobs do you see getting created? Like for example, when robotics industry becomes more mainstream and robots become common in everyday environments, what sort of new jobs do you see? Are there any new jobs that will be created, like Professor Dikal you said? And which major new job segments you think will be there because of the advent of the robotics industry?
Well, I think last year I was looking into a survey that was done by some economy digest. So they were talking about that around 25 different jobs are be expected to be coming up in future by 2045, 50, and so on. So one of the I don't remember their names exactly, but at this time the one of the job which I remember is that was the job for machine psychiatrists. So the argument was this, that we'll be needing machine psychologists and psychiatrists, so that once they are starting to learn new things, so we can't control your machines that learn this and don't learn that. So once they have learned something which is not ethically bound for that given environment, so how to ask them to unlearn? So it's not a code that you're going and you're trying to debug that. So it has to be interactive, and it has to be more like a psychological way. That was something which was very exciting for me. So I think that there would be a number of jobs that would be created, as recently this Dr. Liu was mentioning, that automation never eliminate jobs. It always create new ones. I think there'll be a number of jobs that will be created.
Right.
So the one which attracted me was machine psychiatrist. Yeah.
Right. Thank you. And Dr. Yasir, like in very similar context, like do you think that like robots will like replace jobs more, or they will come as assistive robots more? Like what are the main application areas of robots that you see, for example, in a developing country like Pakistan?
In a developing country like Pakistan, I think robots will change the natures of the job. Employment ratio will not change, because after the industrialization, the employment ratio didn't change. It was like 10% before industrialization and 10% afterwards. Only the nature of jobs changes. So the nature of jobs for humans will become much better. The conditions in which humans are working will improve a lot. We see, especially in the developing world, a lot of people doing very hard jobs in very hot summers and in very bad conditions. And we see all over the world. In Europe, we see that people do not like to do sanitation jobs. In coal mines, we see a lot of accidents where a lot of people get stuck for weeks and they die. So if we can deploy robotics there, we can put people behind controls of these robots and stop people working in such conditions. Also in nuclear plants, we have seen accidents. That is also working in a nuclear plant without even accident is very harmful for humans. They get exposed to radiations even if there is no accident. So if we can improve the nature of jobs of human beings, this will improve the quality of life for human beings. This will automate stuff. I'm sorry, I'm taking longer. I have seen, as a child, I have seen people driving around with animal carts, doing a lot of work, and now they have moved to motorized vehicles. That has improved the quality of work, the amount of work that they can do. The maintenance cost is reduced, and we see those more of those animals in either zoos or in their natural habitats in forests. And like 15 years ago or 20 years ago, all of these animals were deployed inside the cities, doing very laborious jobs in very harsh conditions, and sometimes they were beaten by their owners. So it will not only improve the conditions of work for humans, it will also improve the conditions for animals.
Very interesting, very interesting actually. So I wish the session could go on longer and longer, and it could take 1 hour more. But we are in the last 5 minutes of our session, and I want everybody to be able to say a final word, the whole panel, about the workshop, whatever you feel, and if there are any final comments that you have. So can we start with Dr. Umar?
Dr. Yasir, thanks. Am I audible?
Yes, you are.
Okay. Thanks all, and thanks Dr. Yasir for this wonderful workshop. Really, it was very nice to have all the experienced researchers as well as all the participants. And we have the opportunity to listen these thoughtful discussions and the future of AI, robotics, and stuff like that. And I wish that in the future, in the coming future, as well as IEEE RAS would be conducting more such type of workshops. And I wish and pray for the very best for the IEEE RAS and IEEE in general. Thank you so much, Dr. Yasir.
Thank you, Dr. Dr. Wajahat, if you'd like to say some words.
Sure. First of all, it was very well organized. I would say your team has done a marvelous job. So congratulations on this one. And thanks to RAS Pakistan and all the professors from our international community. So it's always a good pleasure to work with you, Dr. Sir. So looking forward in the future, and looking for more and more collaborations with other academic partners and international industry partners. So thank you very much.
Thank you, Dr. Wajahat. Dr. Yasir, if you have any comments, any insights that you would like to share.
Yes, I would like to thank the organizing team for organizing such a nice workshop. Even though it was online, we felt like sitting in front of each other and talking to each other interactively. The quality of online workshops and conferences has increased over the last year. And it is very nice that we are again and again talking about robotics, and Dr. Yasir, Dr. Wajahat, and Dr. Umar, etc. And Dr. Dikailu also, they are all working for the progress of robotics in the industry, in our societies. Industry is slow to catch up, but I hope with these insights, with these endeavors, with these visibility, we would be able to convince them to progress much faster in the front of deploying robotics in every industry possible. Thank you.
Thank you, Dr. Professor Dikailu, if you have any words, and how do you rate this workshop compared to the others that you've organized in other countries as well?
Thank you very much, Dr. Yasa, and this is so good. This workshop is organized very, very well, and we have so many people participating in this workshop. And sincere thanks to you and many people who are involved in the organization of this workshop, and really appreciate it. And I really hope in the future we can have more collaborations in many different ways, including the workshop, including a special issue of a journal in the specific topic of robotics, for example, or we can just jointly supervise PhD students or research exchange, particularly for young researchers. And young researchers in robotics, they need more support. I'm not sure how much support in Pakistan for young researchers, but I do think mentoring of young researchers to help them in their career is quite important, because they are the star. They are the future stars of robotics in robotics. So, and I really hope we can work together in the future to help more people, particularly in robotics, to help them with their career and to help them with their long-term future. Thank you.
Thank you very much, Professor Dikai, and it's been an absolute honor to co-organize this with you and Professor Kosuge, and with you two being the very famous names in robotics in the world, and like for us to be also able to benefit and to jointly organize a workshop is a very big honor for us. And we hope that we'll in the future also keep doing workshops like this together. And definitely, as soon as the pandemic subsides a little bit, it will be great if you can also make time to travel to Pakistan. And whenever we organize the next IEEE conference, and it would be a great honor for us if you can make time to come here. And likewise, maybe when I'm passing by from New Zealand or Australia, if you have time, maybe I can drop into your place as well if you're in Australia at that time.
Oh, you're warmly welcome to come to Australia, and for the people who are attending this workshop as well, whenever you got a chance to come to here, I know it's far away from your place, but really welcome to come to visit us and then to discuss more and face to face about the robotics research and the collaborations. And I definitely will try my best to visit you and after the pandemic of the current situation finish. So definitely, I really hope this collaboration will continue, and we just to do something we are very interesting and also very beneficial to people.
Thank you very much. And maybe an idea is that we can take a group photo as well. So maybe all of the speakers could turn on their cameras for a minute, if it's possible, and we could unshare the screen so that the pictures can appear bigger, and we can take a group photo. Salia, can you unshare the screen, the slide?
Yes, sir. One moment.
Dr. Wajahat, are you there? We also want to see you.
Yes,
it's possible.
I'm there, but unfortunately my cam is not.
Oh, camera isn't working. Well, you have a good photo on display over there as well, so it looks good like this as well. So, do you see I don't see all the pictures in a cascaded view here. Maybe we can. Okay. Maybe we can change the view and change it to a gallery view. Okay, this looks better. So, smile everyone. Thank you very much. Thank you very much. So we'll share this picture with all of you, and it's been a great time, spent together here. I think Madam Salia, who's organizing the workshop from the center, would also like a word. So Salia, over to you.
Thank you, sir. It's Isma here. So I would like to thank all the panel members and Dr. Sarah for the wonderful session. This brings us to the conclusion of today's workshop. We would like to thank all the speakers for honoring us with your presence and insight on intelligent robots, Dr. Kosuge, Dr. Yasser, Dr. Dikai, Dr. Kazi, Dr. Umar, and Dr. Yasser. We hope everybody learned something from this workshop, and we will be back with more exciting and amazing seminars like this. Until then, thank you so much for joining us. Allah Hafiz.
Thank you. Thank you. And Allah Hafiz. Bye-bye.
Bye-bye.
Okay, thank you.
Thank you. Bye.
Thank you very much.
Bye.
Bye.
Allah Hafiz. Thank you.